Hey, welcome, Jeff Nelson with VegSource. Today I'm bringing you Dr. Peter Rogers. He's a medical doctor. He's educated at Stanford, Northwestern, Harvard. The guy was #1 in his class at med school out of 333 people. He gets 99% board scores every time he takes them. He's got a very impressive background and story, and he's one of the smartest guys I know. And if you don't know him yet, you absolutely want to. Dr. Rogers is on a level with John McDougall, Dr. McDougall. Both these guys are incredibly intelligent. And of course, they're different people with somewhat different fields of knowledge and experience and a lot that overlaps. But this is the first time today that I'm speaking directly with Dr. Rogers, whereas I've known John McDougall for about 27 years and been to his house and so on. But I want to mention once when I was with John, I was trying to recall a study that he'd mentioned some years earlier in a talk. And John knew immediately what study I was asking about. He knew the title, the authors, everything about it. And he said, come here. And we went down into his basement where there's this row of file cabinets. He walked to one, pulled open a drawer, and he found the study in like 10 seconds. And John McDougall, he's got a photographic memory. I mean, he could probably tell you the page number of something that he read 10 years ago. And I think that Dr. Peter Rogers is exactly the same. Dr. Rogers not only has some of the very best information on diet and health, but he digs into all the areas around lifestyle, chemical exposure, things in the environment, and aspects of modern life that can be toxic and which you need to know about in order to try and protect yourself. He also saved my wife's life just this week, and I'm not kidding. I was supposed to interview Dr. Rogers last weekend, but on Tuesday before last, my wife, Sabrina, turned orange. I took her to the ER and she was admitted to the hospital with severe jaundice and acute liver failure. So the specialists worked for some days to get to the bottom of it. They gave her all kinds of tests for hepatitis A, B, C, and E, ultrasound, X-ray, CAT scan, MRI, autoimmune disease tests. I mean, they literally gave her every test that they could think of for liver function, including a liver biopsy. And Sabrina came back negative on everything. The doctors were baffled what was causing her liver to fail. And they were really perplexed. They asked her at different times, do you take any medications, supplements, herbal treatments? And Sabrina said, no, nothing, just B12 is about it. So I emailed Dr. Rogers at one point and I said, listen, we have to reschedule our interview because my wife's in the hospital. And I told him a little bit about it, including that her super high bilirubin numbers and liver enzyme numbers were now starting to come down. And Dr. Rogers wrote back and sent me a bunch of very useful information about liver failure. He sent me a link to an expert at Stanford with a video, and it was really great. Then he sent me a second email. And in this email, he said, I do remember my botany professor telling me to never drink herbal teas because some were toxic to the liver. I also remember from residency some herbal tea causing liver failure. If your liver enzymes and bilirubin are improving, that's a good sign the liver has a lot of regenerative capacity. When Dr. Rogers mentioned herbal teas, I asked Sabrina. She was in the hospital. I was at home at night. But I texted her, hey, are you drinking any herbal teas? And then a light went off. And Sabrina said, actually, she had started drinking this tea in early December, and she was drinking it every day. It didn't have any caffeine. She enjoyed, a couple of strong mugs of this tea on cold nights. And so I thought, aha. So I went downstairs and opened the cabinet and found the tea. And I texted her the name, which was an herb called rooibos. And about 2 minutes later, Sabrina texted me back a link to a case study in a medical journal. It was about a 52-year-old man in South Africa who got jaundice. He had acute liver failure. All his tests came back negative. So in other words, just like Sabrina. And the doctors then reported they figured out that he had started drinking this same rooibos tea that Sabrina had started drinking. And they ultimately concluded that the tea had caused his liver failure. So we searched more on Google, on PubMed, and so on. Came up with probably a half dozen published cases of people going into liver failure after drinking a lot of this rooibos tea. Anyhow, I'm going to do a separate video on all of that. But after we found these studies on tea and liver failure, we told one of the specialists in the hospital who was treating Sabrina, and then he said, a few hours reading up everything in the literature he could find about it and different warnings and publications and so on. Long story short, Sabrina's doctors ended up concluding that this same thing is most likely what happened to Sabrina, that this tea caused her liver failure. And they are probably going to write Sabrina up as a case study. She was in the hospital for a week, and she just got out this past Tuesday, 4 days ago, and she's improving. But My point is, without Dr. Peter Rogers telling me this, suggesting we explore herbal tea as a potential trigger, we might never have figured out what was causing Sabrina's problem. And she might have been discharged from the hospital, come home, and then, started drinking her favorite tea again. So, Dr. Rogers, thank you for saving Sabrina here. I really mean it. I really appreciate that.
Well, thanks.
Yeah. Folks, I cannot overemphasize how knowledgeable about nutrition and health in general that I think Dr. Peter Rogers is. In my opinion, I've read 2 of his books at this point. I've watched many of his videos. He's one of the leading experts in the world. I'm not exaggerating. He's a know-it-all in the very best way. Plus, he's very entertaining. But most importantly, he's light years ahead of the vast majority of doctors and vegan doctors out there. He's written quite a number of books with great information and some with great titles like How to Fix Your Fat Ass in 5 Easy Steps. And I want to urge you to get his newest book that I have here. It's called The Poor Man's Way to Prevent Dementia and Raise IQ, How to Keep Your Brain and Your Boner. Okay, so this could be the most important book that you'll ever read. It's really, I think, the authoritative book on preserving your brain and your Johnson. But I'm going to put a link in the description so you can go check out this book on Amazon. But if you prefer, or if you're too cheap to buy the book, you can watch a series of videos that Dr. Rogers has made on his YouTube channel, where he goes through each chapter and basically tells you everything that's in his book for free. So go and subscribe to his channel. Right now, I'm going to put a link in the description. And then do what I do, which is to binge watch his various videos on all the most important subjects you need to know about in order to live the longest and healthiest lifestyle. I often listen to him when I'm out running. I have been in this for 27 years, the plant-based world. I built and hosted most of the websites of vegan doctors since long ago. We started with PCRM, McDougall, Esselstyn, Michael Greger, and about 100 more. Just, vegan sites and so on. And I would not be giving as strong a recommendation as I am today if I didn't absolutely know that Dr. Rogers is the real deal. One of the many things that I really respect about him is that he has a finely tuned bullshit meter. And by that, I mean he can distinguish between a biased industry study that's going to usually take you in the wrong direction versus actual good science. And this is so important and so rare. It is way too rare, especially in the plant-based world. I've made a number of videos myself responding to plant-based experts who too easily fall prey to corporate science, which is really just Madison Avenue advertising and nothing like actual science. Dr. Rogers even goes through and looks at the work of other experts and other vegan experts, and he makes videos reviewing their bestsellers and sometimes punches big holes in them. I just listened to him deconstruct a book by the neurologist couple, the Sherzais, commenting on their work and their advice on dementia in their book and showing where they got some things wrong. And I think that's really important information to know. And he's very respectful. He gives people their due, what they deserve. He's not demonizing or trashing anyone, but he can destroy poor advice that other experts might give. And then he backs it up with really interesting research. So when it comes to his bullshit meter, I consider Peter Rogers a kindred soul. We all know if you develop a health problem, you probably made a mistake. It's really that easy. I'm not saying, you did it on purpose, but it is somehow your fault because you had bad information or you listened to the wrong expert, maybe the wrong vegan expert, or maybe you had no information. You just didn't know. If you get type 2 diabetes or you have a stroke or heart attack, you probably made a mistake because you probably could have prevented it if you'd had good information and applied it. Sabrina got acute liver failure. She sort of made a mistake. She didn't know what Peter Rogers knew about herbal teas. Now she knows she's not going to make that mistake again. Another example, if you get AFib or myocarditis or, neurological, you probably made some kind of mistake or series of mistakes. I think that's possible. And perhaps the mistake was following the wrong advice again. Maybe someone said, hey, you need to get a cooties prevention shot so you don't get cooties. You get the shot, you get cooties anyway, plus you get myocarditis or something. So yeah, that can happen. You make a mistake, you listen to the wrong people, you didn't do your homework, you got hoodwinked. But my point is protecting yourself is about taking responsibility for your health, identifying smart, trustworthy people who have good information. And for those purposes, it doesn't get any better than Dr. Peter Rogers. And he's not trying to sell you anything. He's giving it away for free on his YouTube channel. And I want to tell a personal story about my dad that illustrates why we all need a McDougall, an Esselstyn, or a Peter Rogers. One of my dad's best friends growing up was a medical doctor. His name was Meyer Friedman. And Dr. Friedman, along with his partner, came up with the type A theory of heart disease, that hard-driving, competitive people with free-floating aggression, these personality traits make them much more likely to get a heart attack. But if they train themselves to be a type B personality, then they could dramatically lower their chances of heart disease. Dr. Friedman was a lovely guy. He did a lot of very important work. I think he was onto something, but I don't think his theory really proved out, because he himself had 2 heart attacks. He had bypass. He died of heart disease in 2001. So I don't really think he found the key. My dad was a case study in one of Dr. Friedman's books, representing a perfect example of a type B personality. So my dad shouldn't have gotten heart disease, right? But he did. In his late 70s, he found himself in the hospital getting balloons and stents and so on. And, you know, my dad knew McDougall and Esselstyn from my conferences over the years that he had attended. So he said, okay, it's time for me to change my diet. And he had great success over the next several years. And then I saw my dad, you know, kind of loosening a little. He would go to a friend's house and eat whatever they were serving. He might have fried calamari at his favorite Italian restaurant, you know, but only once every couple months, he would say. So he was sort of slipping and playing with fire, in my opinion. But one night, my dad was having chest pains. And Dr. Friedman had always said, if you think you're having a heart attack, get an ambulance. Don't have your wife drive you to the hospital, because they can keep you alive in the ambulance. My dad took the ambulance, and in the ER, he was telling the doctor that he'd had chest pain. And the doctor said, you may have had a heart attack. We're going to give you some tests to find out. And just at that moment, the big one hit, the 900-pound gorilla on my dad's chest, who was a left anterior descending, the Widowmaker heart attack. They rushed my mom out. They used paddles to restart his heart, and they rushed him into the cath lab to try and save his life. And I was here in LA. My dad was up in San Francisco Bay Area, and I flew up there and spent the night. And the next morning, the cardiologist came in and said to my dad, you should have died, but you were 50 feet away from a cath lab, so, you know, you lived. And that from that point forward, my dad found low-fat vegan religion. He and my mom, they hired a chef. My dad emailed a menu each week from, you know, recipes from McDougall or Esselstyn's books. Twice a week, the chef dropped off dishes that my mom then, you know, made a salad or a soup and then reheated these. And my parents' house became like the healthiest place to eat on the planet. My dad lived another 7 or 8 years. He got off his heart meds. He had no heart problems, and he died of something else at age 94. And he was sharp as a tack right to the end. What saved him? Well, obviously good luck. And I believe in good luck. That's my religion. And he was saved by the kind of information that people like Dr. McDougall, Dr. Esselstyn, and Dr. Peter Rogers share the world. You can learn to avoid a ton of mistakes from my guest today, Dr. Rogers. So with that, it's time for me to pipe down and hand the floor over to Peter, if I can be that familiar, and ask him to tell us a little bit about himself before he teaches us about preventing dementia. Welcome, Dr. Rogers.
Yeah, well, thanks.
How long have you had your YouTube channel? When did you start that?
Oh, gosh, about 2 years ago. I mean, I initially had started one real briefly when I wrote a book, Straight A at Stanford and on to Harvard. So that was about 10 years ago. I started the channel, but I didn't do anything with it. I maybe made like about 5 videos. But then when I started getting more involved in this nutrition stuff, and I wrote a book about nutrition, my friend said, make YouTube videos on nutrition. I go, yeah, why not? So that's like, and that's
so how many do you have now? How big is your collection?
I got over 1,200 videos.
Oh my goodness.
I just sort of crank them out because I'm a lot of times I'm real busy. I'll get an idea, I'll write down a note card, make a video. So, I mean, when I have more time, I try to put more time into them, and I try to, you know how it is. I'll make a long, really good one, and then I'll make a bunch of quick ones when I get a thought.
Right. No, and I like the variety. Sometimes there's like a 54-second video. I'm going, oh, this ought to be interesting. And then other times, you know, it's an hour, and those are the ones I usually run and listen to at the same time. Well, that is really cool. I also think how you said Alzheimer's might not exist. That was striking to me. And I heard what you said and I thought, wow, and then it made me think of that guy who used to be the president of Stanford, who had to resign because of some fraud in the study he did about Alzheimer's for a drug company or something. And I'm thinking, geez, yeah.
Yeah, it kind of came out of a couple of things. One thing was in my mid-30s, I got fat, and I couldn't believe it had happened to me, but I got fat. I was overworked during my fellowship. I was trying to do 2 fellowships simultaneously, and I'm fat. My mom has metastatic cancer, and my father has coronary artery disease. And I'm thinking, I'm supposed to be a really good doctor. How come I'm fat and my parents are both sick? So I went around and talked to a bunch of doctor buddies. They really didn't have any helpful advice. The attitude was sort of at that time, your mom has cancer, go to the cancer specialist. Your dad has heart disease, go to the cardiologist, and yourself, you're fat. Well, maybe you should take a pill for your cholesterol is a little high, but they really couldn't put it all together for me. And so I started to then read in a lot more detail, started to really try to understand things at a deep level. And what I started to come across was that most of the answers to health, they come from nutrition, epidemiology, and toxicology. Those subjects are not taught in medical school or in medical residency. They're basically outside of conventional medicine. Conventional medicine defines all these diseases as chronic: hypertension, diabetes, obesity, because it can't cure them. It has no cure. It expects to keep the patient on meds for their whole life. But then I saw in the vegan community, they're routinely curing these problems and a whole bunch of other ones. And then I started to learn about disease causation. To cure disease, you want to avoid the thing that causes it. And so I started to realize, wow, there's all this great information. More people should know about this. All the medical textbooks are wrong on all the common diseases. It's not a joke. It's true. It's rather amazing. I mean, at a fundamental level, like, disease theories are important because a disease theory guides how you think about it and what you do to avoid getting the disease. So it's important to get that disease theory correct, because if you don't have that disease theory correct, then you don't know what to do. And typically what the textbooks say is they go, well, nobody really knows. It's associated with aging, probably partly genetic. So, you might as well just take our pill. Hopefully it'll help slow it down. That's kind of like almost every single chapter.
Well, it's amazing how, your background medically is you're a surgeon who works with x-rays and with ultrasound, or tell us a little bit about that.
I did a surgical internship, standard conventional open surgery as an internship. And then I did a diagnostic radiology residency, but I was really all along expecting to go into imaging guided surgery, which is also called interventional radiology. So that means you do a procedure, like let's say a patient has an abdominal abscess. I would use CAT scan to put a drainage catheter in there versus making an open incision. So it's a whole bunch of things like that. And when I did my fellowship, I especially did, endovascular surgery, meaning, inside of blood vessels, like angioplasties and stents in the peripheral vascular system, meaning, the pelvis, iliac arteries, as well as in the legs. So I had a lot of experience then. And I used to think the guys who know vascular disease are the cardiologists, the interventional radiologist, cardiothoracic surgeon, and vascular surgeon. But I don't think that way anymore. I now think of them as plumbers, because all they're thinking about is, here's a blockage. Can we get a stent through it? Can we bypass around it? So they're just trying to solve the problem of getting blood flow distally, but they have really very little interest in understanding, why did this happen? And then I started to read the pathology literature, and that's where you get the real answer, because a pathologist doesn't care. What I mean by that, a cardiologist has to say stents are good, or they'll run them out of town. A surgeon has to say bypass is great, or he'll get run out of town. So a pathologist doesn't care how you treat it. He just says, I look at it under my microscope. It's a blood clot. And as I started to understand atherosclerosis is actually a blood clot, then it all started to make sense to me. And also that the key thing is atherothrombosis theory. So atherothrombosis theory, athero being a thrombus, clot, that will explain everything. And that matched what I had seen in my procedural experience, and also on the imaging. Like when I look at CT angiograms, and then everything started to make sense to me. And I became friends with the guy who wrote the best book ever on atherosclerosis, Gregory Sloop, MD. He wrote a book called cardiovascular pathophysiology and hemorrheology. And it's all about atherothrombosis theory. He's like the pioneer of atherothrombosis theory. And we had a lot of fun talking. And so I'm like, yeah, that matches my experience. That matches my experience. So everything fit into place, because before that, you start reading conventional medicine's cholesterol theory. You're like, how does the cholesterol actually get subintimal? But once you go down the path of atherothrombosis theory, you'll see cholesterol. It's relevant, but it's a subset, and everything will make sense.
You're the guy with the beard on this one? No.
Oh, no, actually, that's Dave Schultz and his brother, Mark Schultz. They're world and Olympic champions.
Oh, okay.
They were both the assistant coaches at Stanford. And the reason I really honor those guys and I'm grateful to them is because, I was having a hard time getting my career going as a wrestler at Stanford. And I was even thinking of quitting wrestling. It's a long story, but Schultz brothers said, You hang out with us. You're going to be fine, Rogers. I go, okay. And I started hanging out. I learned, I just listened to them because they had this experience. And I just did what they said. I wrestled all spring. And next year I came back. I set the all-time record at the schools, team captain, won Student Athlete of the Year award, all that stuff.
Wow.
But so I'm grateful to them. Dave Schultz had incrementalism. He was a kid. He was fat with dyslexia. Other kids would pick on him, like in 4th grade. And he realized he could learn how to wrestle. And he found an exponential advantage. By learning technique, he could get better than people that were much quicker and stronger than him, for example. And the other brother, Mark, what I learned from him was an intensity of focus. When you really want to achieve something, one of the great secrets is you just narrow your entire focus on achieving that one thing. And you get tremendous increased energy and ability by doing that. So you have to like for example, when I wanted to write a book, I'll wake up early in the morning, go to bed early. I won't do anything social for a while. I won't even make a phone call the entire month. And it sounds kind of narrow-minded, but I know from experience, that's what works.
You know, I just love the breadth of your work, of the videos that you do. You drill down, you know, in a beautiful way to a lot of different subjects, but I don't use detergent anymore to wash my clothes. And I credit Peter Rogers with that. So I love how you go into so many other areas too, and look at the research, and you're not just, you know, spouting something, you're actually citing an author or a study or something. And because it makes sense. There's so many toxins in our life that we're exposed to, and there's so little, just like the supplements or the herbal tea world, nobody's like checking it or testing it, and you got to protect yourself. You got to defend yourself. So I love the breadth, the range of things that you tackle.
Yeah, I kind of moved towards that idea of you want to be like Adam and Eve, except keep your indoor heating and plumbing. Be simple. Strength comes from simplicity. Great achievers, they narrow their focus and they go from there, because the more you complicate your life and the more of these modern technical things, they just cause problems for you. And I'm going to go through kind of too how you can avoid them and how you can recognize some of these problems. That's why I think it's important, you know, in the context of dementia, have a theory that explains what to do. So then you can, you know, reduce your risk of dementia, keep your mental sharps.
I love the little, you know, comparison you make to a video game where the character's playing the game and some things, you know, are poison and take away his energy, and other things, you know, he gets it. Give us that again. You know what I'm talking about?
Oh, yeah. Super Mario Brothers and lots of video games. You know, your character going through an obstacle course, and there's some things, if you do them, they're good. You get points, energy points, resilience points. Other things, you make a mistake, you lose energy points. And that's a lot like what health is like. You know, you eat the good food, you get the good sleep, you know, you manage your stress, you get along in all your social relationships. You're feeling good. Your body has increased resilience, and you want that increased resilience because everybody has a problem at some time or other. For example, people sometimes fall and break a hip. Well, if they don't have much resilience, they usually die after they fall and break a hip. If they got a lot of resilience, they probably won't even break their hip in the first place. But if they were to, they recover from it pretty fast, you know? Like I think a good example too, like that Ruth Heidrich's lady, she got a fracture. She was training for triathlons. She got a fracture in her leg, comminuted, I think it was a comminuted femur fracture. They told her she'd never walk again. She's back running in a couple of months. And because, you know, she's got the good diet to heal fast, plus she had the mindset, you know, those things make a big difference in healing.
Ruth is a legend. Yeah, for sure. She's got a great story. Well, unless there's something else you want to tell us right now about your background, you want to dive into it?
Well, yeah, I mean, that's
what else?
Much, so basically I just decided to, you know, become an expert on this, and I really liked it, and I wanted to do something useful. You know, my regular job only requires, you know, like about half my IQ. So I got all this extra energy, and this is the thing that'll help people the most. So I've been enjoying doing this. I just do it as a hobby because it's fulfilling. I think this is where it's really at for optimizing what you can do to help people. So
definitely. Yeah. Well, hats off. Thank you. I continue to enjoy watching everything you got on your channel there.
Do you want me to go show the slides?
Let's dive in. Yep.
Okay, so here we go. And this is basically where we all find ourselves, especially by when you hit middle age. You know, you want to get your act together, the sooner the better. And, you know, the vegan community is real good about diet. The best diet, of course, low fat, low sodium, vegan diet, no oils. But I would also say this is under-recognized, all the problems with toxins. So you want to learn something about toxicology, because that's also an important part of keeping your health. And also EMF is becoming relevant. You want to, you know, decrease your exposure to EMF to the extent you can, especially when you're at home. Because the people who just go down the regular path, standard American diet or whatnot, they end up on a bunch of drugs, and the drugs fail. Then they end up getting a bunch of surgery. It's real expensive, painful, miserable, and they die prematurely. Versus if you follow things right, like the Seventh-day Adventist study, the women lived about 89.5 years, the men 86. And that was the vegans. It wasn't even necessarily health vegans. They were sort of religious vegans related to the Seventh-day Adventists in Loma Linda. But they could even do better than that if they had been so-called health vegans. And then here's what I was alluding to, that basically to try to practice medicine and teach people about health without knowing nutrition, epidemiology, and toxicology, you can't get past being a Lilliputian, okay? To be a Gulliver, you got to know what causes disease, and it's mostly these issues, nutrition and toxicology. And then the benefit of epidemiology is it gives you confidence. You know, 1 billion out of 1 billion rice eaters, they're all skinny. So rice helps make you skinny. 1% of the calories from fat, for example. And here was the images of the Mario Brothers, Super Mario Brothers, you know, going through their obstacle course. And we all go through our own obstacle course in life. And here's a picture of the brain. This is a midline sagittal, so looking at the middle of the brain from the side. And the first thing I'll mention here is what's called the three-part brain of MacLean, also called the triune brain. The brainstem is kind of what we call the reptile brain. A reptile doesn't have to do much. It lays its eggs and then can walk away. Okay, this part right here, the cingulate gyrus that goes into the medial temporal lobe, it's shaped like the letter C, like a Chicago Bears football helmet, and that's called the mammal brain. And it's also called the limbic brain. Limbic means edge, like the medial edge, and it's very emotional. Okay, an animal takes care of its young, nurses its young, a mammal, for example. And so it's got some level of thinking, but it's also very fast, impulsive, and emotional. And then the third layer is the cerebral cortex, the primate brain, or the human brain, much more thoughtful, and especially the frontal lobes, which humans have far, far, far more than any other animal, including chimps. Chimps' brain's about a third the size of ours. Okay, so that enables you to delay gratification, to do the thing you should do, even though you don't really want to, but you know you should do it, and to look at the long-term consequences of an action. Okay, so and then what you can gain from this is if you're feeling emotional and impulsive, and you know you're with your significant other or something, you're like, well, maybe I shouldn't say that, yeah, because it'll cause a fuss for a prolonged amount of time. Don't do that. All right, so anyways, our brain does have lymphatics within the dura. And it doesn't have lymphatics within the brain parenchyma. The reason I'm mentioning this to you is at night, our brain cells, they dump out their waste products, kind of like Victorians dumping out their chamber pot through the window at night onto the street. They dump it out in the cerebral spinal fluid, and it gets rinsed into these lymphatics, and then it goes into the neck, lymph nodes, and whatnot. But the point of all this is your brain can only go offline while you are asleep. During the day, it has to maintain precise neuronal gradients, so it can't go offline. If you were to open up the perivascular spaces of Virchow-Rubin, that's the space around the nerves, and if you were to open that up in the daytime, it would throw off your gradients and the neurons wouldn't be able to function. So what this means is at night, you sleep, you wake up in the morning, and you're as smart as it gets first thing in the morning because your brain cells have all been cleaned. They've expelled their waste products. So that's when you want to do your best thinking. And it makes sense that at night after you've eaten, you don't need to be smart. You can go to sleep. But in the morning, you fasted overnight, you know, you want to be optimal in your thinking to go out and find some food. That's when you should also study or do your complex technical work. Here's a close-up picture. The space around the artery where it penetrates the brain tissue, the brain parenchyma, is called the perivascular space of Virchow-Rubin. And this opens up at night while you are asleep, and cerebral spinal fluid flows in along the artery, and then it percolates through the brain parenchyma. These little brown spots here are the waste products being pumped out by these neurons, and the CSF rinse them over into the perivascular space around the vein. And then this rinses and goes up to the dural lymphatics, and it's expelled from the skull, from the intracranial vault. And that's how the brain cleans itself. It's called the glial lymphatic system, and it's typically abbreviated glymphatic system. A lady named Nedergaard is one of the real famous scientists on that. So if you want to watch her videos about it. Okay, here is the hippocampus, the memory center in the medial temporal lobe. And this is part of the limbic system. This is the main spot for forming our initial memories of declarative things that you can say. Okay, there's other types of memory like procedural memory, how you ride a bike, that you don't put that into words. So that's a different type of memory. But the declarative memory is primarily begun in the hippocampus, and that's useful to know because these hippocampal neurons are very, very sensitive to problems with oxygen and blood glucose delivery problems, and they're also very sensitive to overstimulation, and we're going to talk about excitotoxicity here in just a little bit. Another point about the brain is it's a use it or lose it system, and it is made more for exercise than it is made for thinking. And you know, it's harder to make, this is called Moravec's paradox. It's harder to make a robot that moves coordinated like a human than it is to make a robot do calculus. They could figure that out in the 1950s. They're still just beginning to kind of get better at making them more coordinated. Okay, so what I'm talking about here as well A sea squirt, when it's a juvenile, it has a brain and it swims around like a tadpole. But when the sea squirt is an adult, it attaches to a rock, it becomes a filter feeder, its brain is reabsorbed. You know, it does. If you don't move around, you don't need a brain. You know, why do animals have brains but plants do not? Because an animal moves. As soon as you move, you have to make a value judgment. I shall go towards the food, the fruit tree over there. I'll avoid the potential danger over there, a bunch of coyotes. You have to navigate your path, avoid obstacles. You have to remember how to get back to where you came from. So it requires a brain. And so one of the best things you could do to age well and maintain your cognitive function is to exercise a lot. Good to do some aerobic work every day, at least. Even little things, you know, when the phone rings, if you're at work, stand up while you talk on the phone. Take the stairs instead of the elevator. Park farther in the parking lot. Do all kinds of little things to keep yourself moving. Okay, so here is just two major patterns of atherosclerosis. The first one is the Western pattern from eating high-fat diets. They get a lot of coronary artery atherosclerosis and a lot of internal carotid artery in the neck, cervical carotid, origin carotid, right here is where they typically get. There's another pattern that's been called the Asian pattern of atherosclerosis. You know, back in the 1960s, the Japanese ate a very low-fat diet with the 1% of calories from fat with the white rice, but they had lots of sodium in their food, like, 12, 14 grams a day. And they also smoked a lot of cigarettes. And so that caused high blood pressure. So hypertension alone will have a tendency to cause intracranial atherosclerosis, increasing the risk of a stroke. Okay. And a lot of, Americans, of course, they eat both. Some of them are smoking, some of them are eating tons of salt, and they'll get both intracranial and extracranial atherosclerosis. Okay. Here's just a quick summary of the dementia theories. I call this, Alzheimer's dementia, the so-called BAB theory, beta amyloid BS theory. Okay, now why do I say that? Here's the deal on Alzheimer's. I don't even like the word Alzheimer's because, first of all, what's the historical finding? You can ask the patient to diagnose it. There is none. Okay, what's the physical exam finding? There is none. What's the reliable lab test? There is none. Okay, well, what's the reliable imaging test? They're going to tell you, severe atrophy of the medial temporal lobe and the parietal convexities, but we hardly ever see that. I've looked at many thousands of brains. I hardly ever see that pattern, okay? Then they'll say, well, we could do a nuclear medicine amyloid scan or something, but that's not reliable. You can get that in a patient who's not demented and vice versa. Then you say, well, of course, at autopsy, pathognomonic, neurofibrillary tangles, intercellular, senile plaques, extracellular. Not necessarily. You can see that in a normal patient, and you can have you can have a patient who's demented and not have that. Okay, so it's not reliable. It can lean you one way or the other, but it's not a solid thing. All right. So I think beta amyloid does play a role in causing dementia, but it's not an initial starting thing. It's something that happens, later in the cascade of damaging processes to brain size. Okay, then there's the buy my supplement or you'll die theory of dementia. I think that's overrated. I don't think omega-3s are that important because a lot of people, in healthy populations didn't go searching for that. Now then I call it the FFUE, fructose F's up everything theory of Lustig and Johnson. And I'm kind of kidding here, but what I'm saying is, yes, high fructose corn syrup is a problem, but you can't explain away all these other problems just with that. What I see in the pattern of nutrition is, if somebody's trying to promote meat, they'll tend to say, oh, the problem is fructose, or they'll say it's omega-6 cooking oils. And what I'm saying is there's multiple things that contribute to causing atherosclerosis and plugging up arteries. So I do think there's problems with high fructose corn syrup. Now, the fructose in fruits is not so bad. I mean, I actually think fruits are good, but you do have to be careful. If you're exercising a lot of the really fit, top-notch marathoners, triathletes, they'll eat tons and tons of fruits. But if a person's relatively sedentary, one does have to be careful because it tastes so good, you can easily just keep eating large amounts of it. I can eat a giant bowl of starch and be kind of full. And then if you put more starch in front of me, I couldn't eat it. But if I get a big bowl of fruit, let's say a big bowl of blueberries or something, I could eat 60 ounces of that. So my hunger goes away when you got fruits in front of you, so you can keep on eating and overeating. Okay, to lose weight by eating fat and caffeine helps sleep. I'm kind of joking here, but what I'm saying is there's a lot of people talking about ways to prevent dementia, and they're encouraging people to eat all this fat, to eat nuts and seeds and chia and omega-3s and olive oil's fine. You eat all that fat, it's going to be hard for a lot of people to stay skinny. And I also see a lot of people saying, oh, caffeine's good for you. Caffeine people are healthier. It's fine to have 3 cups a day, and you can have the last one at 2 o'clock. It actually has a 6 to 8 hour half-life, and I recommend 0, not 1 drop. It increases your blood lipids. It causes insomnia. Even if you sleep, you don't sleep as deeply. We talked about the glymphatic system being essential to kind of clean out the waste products of your neurons, including beta amyloid. I think it's a bad idea. Okay, the next thing is I call it the 36 HOR problem, which kind of sounds like you can pronounce that one for yourself. Latau. Okay, so what am I kidding? I'm kind of kidding here, but what's this? It's called 36 holes in the roof. There's a couple of the proponents of dementia theories who claim that you got all these different holes in your roof, and so you gotta take all these lab tests. I call it all these lab tests out the wazoo, and I'm laughing because it's a way to make a lot of money. Okay, and
Yeah.
don't get me wrong, there are multifactorial things that contribute to it, but be careful when somebody says you got to take 20 different lab tests. It's going to cost you a ton of money, and then you got to take all their supplements and pills. Be careful with that because it costs you a lot of money. And I'm going to show you that I think that what you can do, you don't even need to spend any money. All right. And then ABBA. ABBA is not just a Euro pop music group or God the Father, all because bad aluminum theory. And I'm kind of joking here. Aluminum is a major neurotoxin. Okay. And this guy actually, his nickname is Mr. Aluminum. He's devoted his whole life to research. And Dr. McDougall and, Jeff have given excellent lectures on it. And aluminum is a major neurotoxin, but there's just a lot of other things going on. Okay. So we're going to get to some of those. Excitotoxicity. This kind of was really put on the map in the 1960s by John Olney, and he found that this MSG was being put in large amounts in baby food. Okay, then Dr. Blaylock, Russell Blaylock, his father died of Parkinson's, and he felt it was related to excitotoxicity. He wrote a very good book about that in 1997, Excitotoxins: The Taste That Kills. Okay, so that was a very good book, and he had some good lectures about it. Subsequently, Dennis Choi and Mark Mattson have done good research on excitotoxicity. So it's a major thing, but for them, it was a relatively compartmentalized thing. I'm going to talk some about excitotoxicity as well, but put it into a bigger perspective. Calmodulin theory of calcium, Danton O'Day, sort of a researchy focal thing. It's all relevant. It's all true. But again, I think what it needs to help a regular person be able to benefit from this information has to be put in context. We're going to do that in this talk. Omega-6 cooking oils. This especially comes from Tetsumori Yamashima. He was given the task of why are so many Japanese people becoming demented now? And he figured it out that it appears to correlate most tightly with the omega-6 cooking oils. And he has a whole way to explain that. I don't think we're going to have much time to get into that, but I do think he's right about it. Basically, they undergo lipid peroxidation and they cause chain reactions that produce a toxic aldehyde, hydroxynonenal. And then that leads to activation of what is called calpain-cathepsin protease enzymes that destroy cells and lead to apoptosis, programmed cell death. Apoptosis means like the falling off of a leaf. And it's a way to describe when a cell that dies gradually such that it can recycle itself, recycle its internal organelles, if you will, so those chemicals can be used by other cells. So gradual cell death, you can't see it at imaging. You just see atrophic shrunken brain. You can't see it at autopsy either. You just see fewer than expected neurons in a given location. Okay, leaky gut. That becomes relevant because some toxic chemicals get into the blood, especially the gram-negative bacteria making LPS, lipopolysaccharide, the gram-positive bacteria making LTA, lipoteichoic acid, and that will cause an unusual pattern of clotting. I'm going to show that in a little bit here. The EMF theory and the no theory. So what is this about? EMF is electromagnetic fields. Martin Pall is both a physicist and a biologist, and he does a good job of explaining the relevance of that to brain health. And the main point is that exposure to EMF, like holding your cell phone up to your head, it opens up voltage-gated calcium channels. So just remember, it increases calcium in the cell cytoplasm. You don't want that. The no theory is more of the same, but I'll get into that later. That's kind of a complicated subject. And that just means nitric oxide, peroxynitrite. And the way people get confused is everyone's like, well, I heard nitric oxide is a good thing. Didn't, Caldwell Esselstyn say it's real good for us? And Nathan Bryan. Yes, it is a good thing when you're talking about it in your arteries, endothelial nitric oxide. But it can be overdone inside the brains themselves and the immune system. So there's three main types to know about. There's endothelial nitric oxide, there is neuronal nitric oxide, and there's also inducible nitric oxide. And so the endothelial one, that's a good one. And everything that Esselstyn said and Nathan Bryan, that's all good. Okay. But there's a separate issue with it in the brain where it can be a problem. And it'll be activated for different reasons. The mouse equivalent theory. Now, this was a real turning point in dementia thinking. And this comes from a guy named Jack Delatorre, PhD. I'll show you a picture of it and it'll make sense in a moment, but this really turned things around in dementia because I personally think this beta amyloid theory has been damaging to the research of dementia because you can't go anywhere with it. When I tell you beta amyloid elevation causes dementia, what does that make you think you need to do? Nothing. You're like, oh yeah, okay, what am I going to do? Okay, versus when you hear Delatorre's theory, I'm going to talk about it in a moment, it starts becoming obvious what you should do. And then the last one is my theory, neurovascular uncoupling. And what I'm going to do is I'm going to talk about, it means LAB is learn about the brain, run away from toxins. I'm going to talk about how you can recognize something that's toxic to your brain and avoid it and how this puts together all the other theories. Okay, just here's this one article on aluminum. Aluminum causes necrosis, death of pancreatic islet cells. Those are the ones that make insulin. So it contributes to causing diabetes and insulin resistance. Aluminum is pretty ubiquitous. It's in tap water. Sometimes it's polluted in the air and, the trails overhead with the chemicals. And it's in a lot of foods. There's aluminum foil. Some people cook on aluminum. Sometimes you go to a buffet and it's stored in aluminum containers. Okay, so here's Delatorre's theory. And this is really important to get, and it's real simple. He would tie off the carotid artery in the neck of the mouse. Carotid arteries are the main blood supply to the brain. There's one on each side. And middle-aged and older mice would be demented 2 months later. And when he did an autopsy on him, he expected that there would be a big stroke on the same side. He tied off the carotid, but there wasn't. The brain was just shrunken. That's called, atrophy, and it's due to apoptosis. So he did a whole bunch of other experiments. He tied off the middle cerebral artery, a whole bunch of different branches, and every time he got this same pattern of areas that have diminished blood supply but haven't completely lost their blood supply. They gradually shrink over time from apoptosis. And you would say at first, well, so what? How many people have severe carotid artery stenosis or occlusion? Not that many. Okay, but there's lots of things that are like that. Lots of people have atrial fibrillation, AFib, and then they get about, let's say, 25% decrease in ventricular filling, decreased chronic cerebral hypoperfusion. It's also called the vascular hypothesis of dementia. Really sort of like the vascular hypothesis originally of so-called Alzheimer's disease. All right, but so AFib, decreased cerebral perfusion. Congestive heart failure. Lots of people got CHF, decreased cerebral perfusion. If you got, a lot of people have aortic stenosis, narrowing of the aortic valve or regurgitation when it leaks backward upon itself because the valve doesn't seal off effectively. Chronic cerebral hypoperfusion. A lot of people have a drop in cognitive function after open heart surgery. CABG means coronary artery bypass graft. And so, for example, my father ended up going for open heart surgery. That was before I knew enough to tell him not to do it. I knew a little bit. I knew about Ornish, but I didn't, know about Esselstyn yet, and I hadn't read all the history of it. So, and his cardiologist, surgeon kind of pushed him to do it. And my dad came out of it all fine. But, for example, I stayed with him in the ICU, and they were running his pressure like at 90/60. And I couldn't believe how low they were running his pressure. But they said, well, we're doing that because we don't want him to bleed out the anastomoses, the connections of the graft. And he came through it fine. But somebody who had more intracranial atherosclerosis, my dad was probably about as healthy a patient as they ever get. They might not tolerate that well and come out of it demented. Okay, diabetics, they used to check their blood sugar, about 2-3 times a day with a needle, but have no idea what was going on at night. Now they've got these CGMs, continuous glucose monitors, and they found that a lot of these people are really dropping their sugars quite low at night. And that puts them at risk for brain damage from hypoglycemia. A lot of these obstructive sleep apnea patients, they can drop their oxygen. So they go for sleep studies. They put a pulse ox on their finger at night. They can drop their oxygen levels, oxygen saturations quite low. Okay. And you can imagine, too, if you got a baseline disease and you superimpose upon that a high-fat diet where the red blood cells are sticking together, sodium, a lot of dietary sodium when you're vasoconstricting, you can add up all these things that contribute to dropping the amount of oxygen and glucose delivered to the brain cells. Okay, so here is the internal carotid artery coming up into the brain. It'll bifurcate. There's an anterior cerebral artery here, which I didn't draw just to keep the drawing simple. Then there's a middle cerebral artery going out this way, and it goes up around the convexities. Okay, so these are the convexity branches of the MCA, middle cerebral artery. Right here are called the lenticular striae. Going into this area right here is called the basal ganglia. And severe hypertension will sometimes shear off the origin of one of these vessels or lead it to be also atherosclerotic and plugged up with atherosclerosis. So this is a real common spot to get strokes, and they're often kind of linear and vertical. They call those lacunar infarctions. Infarction means dead brain. Lacunar means like a hole. So there'll be like a cylindrical hole in the brain right where one of these arteries is occluded. So that's common from severe hypertension. But there's another problem. Why do we get elevated blood pressure? Why do we have blood pressure? To get blood to the top of our brains. Okay, now you have to be careful. If you overtreat hypertension, you won't get enough blood into these arteries. And I drew a skull and crossbones here because I see what are called silent strokes or minor strokes in this area all the time. In any given day, I'll see like 1,000 of them, okay? And some of them are more symptomatic than others. Some of them just cause a so-called senior moment, if you will. All right. But the other thing is when the blood pressure is too high, it's hitting at these arteries very hard. And they try to protect themselves by laying down a lot of collagen, fibrotic tissue, scar tissue. And that scar tissue will also contribute to decreasing the amount of oxygen delivered to the neurons in this area, the brain cells. Okay. So you're kind of damned if you do, damned if you don't. With hypertension, you're screwed either way. Does that make sense? If your pressure is really high, you're at increased risk for microbleeds or even a major bleed in this area. And if your pressure is too low, you overtreat it, you can drop blood supply to these penetrating arteries, which don't have good collaterals, and you can get these silent strokes and what is called the association deep white matter of the brain. All right. At the level of the ventricles, it's called corona radiata, like a crown, corona that radiates in a circle. Centrum semiovale is the top part above the ventricles. These are the ventricles that contain the cerebral spinal fluid right here. And above that, because you're in the center of the brain and it's shaped semi-oval. Okay. All right. So here is hypertensive bleeds. These are cerebral microbleeds from hypertension. All these little black spots in the center of the brain. Out in the periphery, though, can still be due to hypertension, but this is where amyloid angiopathy, these are microbleeds associated with so-called Alzheimer's, can occur. But one of the points I'd like to make, I see them in any context, and I've seen people in their 40s with a bunch of these. You don't have to be old to get these. And what I'm saying is I think hypertension causes them everywhere. And I also think there's a spectrum and an overlap between cerebral amyloid angiopathy and hypertension, okay? So that's important. And the same people who get hypertensive hemorrhages in the eye, they get this in their brains as well. Now, a big parenchymal hemorrhage right here, like interparenchymal hemorrhage, I don't see those very often. I could, go a couple months and not see one. Those are rare, but, they can be obviously devastating, but they're relatively rare. All right, now here's what I see all day long every day. And any given day, I'll see 1,000 of these. All these white spots are small strokes. Normal brain parenchyma should look like this up here. So all of these are strokes. And then here, when you see them kind of all a bunch together, that's like coalescent strokes. And these are the things that will cause progressive cognitive decline. But most of the demented brains I see, they really don't have too many of these. They just have progressive enlargement of the cell side. This is cerebral spinal fluid here. These are the ventricles with cerebral spinal fluid in them. And these just keep getting bigger and bigger. All these cell side, the ventricles keep getting bigger and bigger. So it's progressive atrophy. And this fits for the dilatory theory as well as, my theory which is basically like just an expansion of the dilatory theory and the calcium hypothesis. All right, so here's a normal capillary. And these are red blood cells traveling through the capillary. Typical RBC is about 7 microns. Typical capillary diameter is about 5 microns. That's worth knowing. And the relevance is that the RBC has to deform itself a little bit in order to pass through the capillary. As it passes through these spindle-shaped cells here, and that's the little nucleus right there, those are the endothelial cells that line the capillary. The yellow structure here is the basement membrane of the capillary. And then just beyond that are these muscle cells, the vascular smooth muscle cells. The green ones, there's a little nucleus there. And the oxygen has to travel across this basement membrane, across the muscular part of the arterial capillary wall, and then diffuse over to the neuron to deliver oxygen that'll be used to make energy. And what I'm saying here is when you get diabetes, you get glycation and progressive thickening of this capillary basement membrane. That's going to make it harder to deliver oxygen. So there's more blue circles up here than down here because it's becoming more difficult to deliver oxygen. In order to protect itself and compensate for high pressure, you'll form more vascular smooth muscles as well as lay down more collagen in this arterial wall. So that's going to thicken the wall, and it's going to make it harder for oxygen to diffuse from the red blood cell to the neuron. So the chronic worsening of capillary wall, arterial wall thickening due to hypertension and diabetes are major contributors to cognitive impairment. Okay, I can tell you like more than 9 out of 10 of my patients that are demented, they've got diabetes or hypertension or both. One thing red blood cells have is a negative charge on their outer surface. That's called a zeta potential. And it's a good thing because they repel each other so they don't unnecessarily clot. But there are molecules that have a positive charge on their outer surface and are big enough to hold the two red blood cells together. That's called overcoming the zeta potential. And things that'll do that is LDL cholesterol. That's why cholesterol is a risk factor for atherosclerosis. And it's the most common risk factor because tons of people in the Western world, most Western world people have elevated cholesterol. The average cholesterol of an American is, in the ballpark of 220. Okay, the next thing is fibrinogen, which is a clotting protein, and that's also elevated with acute stress. So there is an increased risk of clotting during acute stress. In addition, that's also why I don't like caffeine, because caffeine elevates fibrinogen. It's one of the acute phase reactant proteins. Caffeine elevates the same hormones as psychological stress and sleep deprivation. So I consider them, stress equivalents. Also uric acid and excessive amounts of dietary fructose, also dietary meat, but dietary fructose will cause an elevation of uric acid that can also function as a bridging molecule to stick the red blood cells together. So it's going to stick them all together, and it's going to make it then, they're like, rouleau formation is the French word for stack of coins. Once they're all stuck together, it's harder to pump them through the arteries and the capillaries, so blood pressure has to go up. When blood pressure goes up, then there's more injury to the arterial wall, which secondarily leads to more clot formation and more compensatory reactions of the arterial wall. Also, IgM antibodies can stick things together. That's why acute infections increase the risk of forming blood clots that can cause heart attack and stroke. One of the things that generates the zeta potential is the sialic acid. You can basically think of it as like a glucose molecule with a carboxylic acid on it. There's a little more to it than that, but that's all we need to know. It has a negative charge on it. Okay, so sialic acids are typically at the end of what are called glycosaminoglycans. And I'm sorry for all the fancy words, but all it really means is your arterial wall and your individual cells have negative charges around them. And this is all a good thing because they all repel each other, so you don't form clots when you're not supposed to. Okay, and heparin sulfates, the sulfates are, here's like a typical sulfate. You got a lot of negative charges on them. So you get this whole negative charge wall along the surface of an artery. In addition, water has a bit of a dipole to it, meaning that the oxygen is a little bit negative charge, the hydrogens are slightly positive charge, and that attracts them to the negative charge. The hydrogens, the negative charge of the glycocalyx. Glyco means sugar coat, and it just means the outer surface of a cell. Okay, so what this means is it's really slippery, and that's exactly what you would want. It's slippery because of the water, and it's also repellent to the red blood cells because of these negative charges on the sialic acids, the heparin sulfates, and there's also cholesterol sulfates. So the net result is RBCs will travel through that capillary without sticking to it and forming a clot, exactly what you want under normal conditions. Okay, the spleen is like the graveyard for red blood cells. After 120 days, about 3 months, red blood cells will go in the spleen and they'll be lysed. Okay, and the reason that happens is as a red blood cell gets older, it gets stiffer. And there's a couple of reasons for that. One of them is it gets more glycated. There's more sugar molecules irreversibly attached to it that stiffen it, so it can't deform to pass through a capillary as well. In addition, there's a phospholipid called phosphatidylserine, which moves from the inner membrane to the outer membrane, and that stiffens it as well. It's called phosphatidylserine externalization. So the typical capillary in the body is about 5 microns. Typical capillary is about 3 microns in the spleen, so it's harder to get through there. It's like doing the limbo. And, a stiff RBC will have a hard time getting through that, and then it'll get removed by the macrophages in the spleen. The higher somebody's hematocrit, the thicker their blood, the more higher the blood viscosity. And this picture right here is a secret of why women live longer. Because a woman, when she's premenopausal, she menstruates every month, and it's like a therapeutic phlebotomy. It lowers her hematocrit. Hematocrit is a percentage of cells in the blood that are red blood cells, okay? So a higher hematocrit means that you're going to have thicker blood. The vast majority of cells in the blood are red blood cells. Like there's over 700 red blood cells for every white blood cell. So your higher your hematocrit, the thicker your blood, and the more high risk you are for high blood pressure, for hypertension. In addition, when red blood cells first come out of the bone marrow, they're made in the bone marrow, they're more flexible and deformable. Like we just said a moment ago, they're less glycated. They got less phosphatidylserine externalization. So a woman not only has a lower hematocrit, she's also got more flexible red blood cells to pass through her capillaries, and that further lowers her blood pressure. Okay, so that's why women live longer. They're protected. They got about a 10 or 15-year advantage on men for not having had hypertension typically. But the catch is if a woman has a hysterectomy at a young age, let's say before the age of 35, then she's markedly at increased risk to have hypertension, often severe, because also a lot of times women are not aware of it. As a guy, you've got a friend who became impotent in his 30s or 40s. He's on Viagra. You got another friend who had a myocardial infarction, a guy from your high school, and you're like, wow, I better get my act together. This could happen to me. Whereas a woman, she probably doesn't have any premenopausal friends, girlfriends who've had cardiac events. Women don't worry about being impotent. And the reason I go through all this is I'll look at a demented brain. I see a demented young female. First question is she a drug addict? Is she an alcoholic? Did she have head trauma? Okay, and then when it's none of the above, next thing I look at the surgical history, and quite often that's what it is. She had a hysterectomy at a young age, most often due to fibroids. And where does that come from? Because she's got increased estrogen levels. Why she got increased estrogen levels? Because she's eating meat, because she's using a bunch of personal care products, plus there's estrogen chemicals in her tap water. I'll talk about that more later if we got time, but there's a lot of reasons why people get exposed to a lot of estrogenic chemicals. The only important thing on this slide is that the endothelial cells make nitric oxide. Nitric oxide is a gas that diffuses out of the endothelial cells that line your capillaries and arteries, and it causes the platelets to not clot. It prevents clotting of your platelets. In addition, it diffuses into the arterial wall, and it enters the vascular smooth muscle cells, and it causes them to relax, which means to dilate. So that opens up your artery. That's all good. That's what you want. There's other things on an endothelial cell that have a similar net effect, but the important thing to know about is nitric oxide. That's all you really need to know about. Nitric oxide, you get it. First of all, your endothelial cells make it. They have an enzyme, eNOS, endothelial nitric oxide synthase. Okay, you also get some from sunshine. You got nitric oxide precursors underneath your skin that are activated by the sun. That's why you feel good. You walk out in the sun, you get this total body vasodilation. It's pleasurable. It's nice. We're made for that. But the next thing is you get it from eating greens. And these become more important as you get older. Nitric oxide production in endothelial cells goes down. I think a lot of that's just due to Western populations and their diet and whatnot. I don't think it's quite as bad as is often told to the public, okay, that you're going to lose 50% of it by the time you're 60. I think that you do lose some, but not as bad as that because, if you're eating a healthy diet, you're not going to lose it as rapidly as somebody who's not. Okay, so what's the point? The greens contain nitrates. And the nitrates, there's bacteria in the back of the tongue that convert them to nitrites. This should be an I right here, and that's NO2. Nitrates are NO3, nitrites are NO2. Then in the stomach acid helps convert it to nitric oxide. It goes into your arteries. It can travel along hemoglobin. You get the systemic vasodilatory effect. Okay, so what's the point? Well, you don't want to use F- toothpaste or mouthwash because that'll kill the bacteria in the back of your tongue and you won't be able to carry out this first step. If you're taking proton pump inhibitors, for example, for gastroesophageal reflux, you could lose the ability to carry out this next step to go from NO2 to NO. So those are things that can have an atherosclerotic effect. Does that make sense? So what I'm saying here is brushing your teeth with F- toothpaste could worsen your high blood pressure and increase your risk of atherosclerosis problems. Okay, now this is a study, and I think you mentioned earlier, Meyer Friedman and Ray Rosenman was one of his partner ophthalmologists. And initially, there was a guy named Peter Kuo, cardiologist in Philadelphia, and he found with saturated fat that when a person would eat saturated fat, he would check their blood lipids every 30 minutes. He actually took a bunch of patients with known cardiac angina, meaning they get chest pain on exertion. And what he found was after eating a high-fat meal with saturated fat, between about 3 hours to 7 hours during peak lipemia, highest blood levels of fat, that they would get the most onset of chest pain. Peak angina was the same thing as peak lipemia. Then, that was all the work Ansel Keys in the 1950s. Saturated fat's a cardiac risk factor. So they tried all the omega-6 cooking oils in the 1960s, PUFAs, polyunsaturated fatty acids, and thought maybe these will be cardioprotective. But as it turns out, and some of these studies later were then done by Meyer Friedman and Ray Rosenman, they found that you would get even more prolonged elevated lipemia. And his workers were pissed off because they would start, let's say, at 8 o'clock, 9 o'clock in the morning, and the patients would still be in high levels of blood lipids, into the evening, okay? All those workers wanted to go home. So anyways, the point was the PUFAs were worse than just the saturated fat. Omega-6 cooking oils are much worse for health than is widely recognized. Okay, and then the ophthalmologists, Rosenman and Friedman, they would look at their eyes with this 80-fold magnification, and they could see capillaries sort of shutting down. And, I think they also fed some sodium in there, vasoconstricting, but also occluding transiently. You don't want that. Usually they'll open up back so the person doesn't go blind all of a sudden, but it's not a good trend. Okay, rouleau formation. And here, that just means, stack of coins in French. So when you push this stack of coins like a triple-decker submarine sandwich through an artery, you can see pressure has to go up to get that through. Now, here's what normal blood flow should look like. It should be laminar. The red blood cells are in the center at the fastest velocity. Right next to them is the white blood cells. And then on the outer part, the black arrows there where my thumbs are, that is the plasma. And that is what runs along the glycocalyx of the cells that line the arteries, the endothelium. All right, so here's what happens at a bifurcation point. This is where atherosclerosis starts. It starts at bifurcations. So the blood flow's coming up, and it's going to hit the median divider. This is the arteries of the neck: internal carotid artery, the ICA; external carotid artery, the ECA. So ICA goes to the brain, ECA goes to the face. And when the blood comes up, it hits the median divider, and then some of it bounces off and creates turbulent flow. Turbulent flow means chaotic flow. And there's also eddy currents, which means retrograde flow along the outer wall. And the point of this is, if the blood pressure is excessively high, you will then get an excessive amount of turbulent flow and an excessive amount of eddy currents. Well, the endothelial cells, they've got these cilia-like extensions as part of their glycocalyx that can sense the flow. And if they sense abnormal flow patterns, excessive turbulent flow or excessive retrograde eddy currents, that confuses them. They think there's been a vascular injury. They start to shed their antithrombotic glycocalyx, and they start to express prothrombotic molecules on their cell surface, like VCAM, vascular cell adhesion molecule, for example. And they'll start to form clots. You don't want that. This is atherosclerosis. The body will reach a steady state where it's partially forming clots and removing clots. And the more the hypertension is under control, it helps the body to keep up with this. Okay, but you don't want to overtreat hypertension, or you drop perfusion of the upper part of your brain, you predispose yourself to a hypotensive stroke. Okay, so anyways, this is then the steady state, and it can go on for a long time, but gradually as they get older, they might lose the ability to compensate, and now they're at increased risk to form bigger clots here, and little pieces break off and travel distally. That's called to embolize, and those will cause strokes. Okay, but this is where atherosclerosis starts, at bifurcation points due to abnormal blood flow. And this is why hypertension is the #1 risk factor for atherosclerosis. Okay, high dietary fat's also going to be right up there as a top risk factor, and high cholesterol is because it's going to thicken the blood, causing the pressure to go up, causing more abnormal flow. The two things go together. All right, so you can see here's relatively normal arteries with pretty wide open central channels. It's called the lumen. Okay, here is accumulation of atherosclerosis along the wall, and here's a person with relatively heavy atherosclerosis. You can see this yellowish material is part of these old atherosclerotic plaques, all right? Now, that's going to be relevant because you can imagine there's going to be branching arteries coming off this wall, and if all of this is filled up with clot and plaque and debris and scar tissue and collagen and fibrosis, that artery that comes off the wall is going to get occluded. That's a major problem. I'm going to show you here a normal variant. At the base of the skull and at the base of the brain, you have something called the circle of Willis. Willis was the anatomist who described this. So here's the internal carotid artery coming up, goes off into the MCA. So here it is on this side, goes off in the middle cerebral artery. There's a small connecting artery between the anterior circulation, which is the carotids in front, and the posterior circulation is the vertebral arteries in the back. And then there's this connector artery. It's called the posterior communicating artery. Normally, in an adult, it's very small. Sometimes it's even completely absent. And in a baby, though, it's large. In a fetus, it's a very large vessel, and the posterior circulation of the brain, like to the occipital lobes, is fed off of this artery, off the anterior circulation. Okay, then normally, and in the course of fetal development, this will regress and shrink. All right, but sometimes it doesn't. Sometimes it stays big. So that's called normal variant persistent fetal type posterior communicating artery. And the relevance is, when the ICA into adulthood is supplying the main blood supply to the posterior cerebral artery branch here, the basilar doesn't have much work to do, so it stays very small. It's hypoplastic, okay? So when you got a hypoplastic basilar like this, so here's a hypoplastic basilar with bilateral persistent fetal PCOMs, posterior communicating arteries. What that means is the vessel traveling along the front of your brainstem, like we looked at the 3-part brain earlier of McLean, sitting in front of the pons, the belly of the pons. This is all part of your brainstem, midbrain, pons, and the medulla. So if this is a small diameter vessel, it's prone to accumulating atherosclerosis along its posterior surface, and then its little branch arteries that go into the pons, they can become occluded by this atherosclerosis. So what I'm saying is it increases the risk of a brainstem stroke. So here's what it looks like. All these little white spots are strokes. So let's say you got a small hypoplastic basilar artery, and so then it gets atherosclerosis along its surface, and then it starts occluding its penetrating branches that go into the parenchyma here. Pop, 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 pop. Pop, pop, whole bunch of strokes. Okay, so what I'm saying is none of us knows if we have this anatomy. I see this anatomy, I see it. I usually see about one every other day. Sometimes I'll see two in the same day. None of us knows if we have this unless you've had a CTA, MRA, CAT scan angiogram, or a MRI angiogram. You don't know if you got this. So it is wise to just assume you've got it and be careful about your risk factors. So a person who's got this type of variant in their brain and they could have it elsewhere in their body is an increased risk for stroke. And probably in the microcirculation, you got the same thing. You're just not aware of it. All right, so now what I'm trying to say is it's the same thing in the heart. So here's a typical, ascending thoracic aorta, left main coronary artery comes off of that, bifurcates into the circumflex coronary artery and the left anterior descending artery, okay? These are called the epicardial coronaries. They're on the outer surface of the heart. And the big proximal part, you can, do a bypass from here to here, a bypass from here to here. You can put a stent into these big arteries, but guess what? You've got all these penetrating arteries that go into the muscles, okay? These are called the intramuscular arteries, intramyocardial arteries. You can't do anything with those. You can't surgically bypass those. You can't stent those. So what I'm saying is, sooner or later, you have to address the fact that you have to treat the microvasculature. And there's only two ways to treat the microvasculature. Either you optimize your diet or you hope you can control it with pills, okay? And it's wise to certainly optimize your diet to avoid occluding this microcirculation. People can have a totally normal cardiac cath, but have a heart attack and have angina because they've got occlusions in their microvasculature. That's important to know. You can also get variants where you'll have a trifurcation here, like a ramus intermedius. And what that means is that these other vessels are going to be smaller. If there's 3 of them dividing flow up instead of 2 of them, they're going to be smaller, harder to stent, okay? So what I'm saying is stents don't, if you got chronic angina, if you have a acute heart attack right on the spot, and they get across the thrombus, the clot, they can save your life. It's a great thing. But most of these chronic angina patients that get stented, it doesn't really change their longevity, okay? And same thing with the coronary artery bypass graft. Overall, it really doesn't cause a significant change in their longevity, how long they're going to live. So the best thing is like, the Esselstyn diet. All right, this guy is Chris Knob. He's an ophthalmologist, and he kind of likes to recommend people eat meat. He thinks meat's a good thing. And excuse me. So he kind of will talk about what does he think is the main problem in the dietary health of Americans. And actually, he's a real smart guy. He checked the dietary health of people all over the world. And he showed that Americans since the 1800s have gained about 50 pounds, the average man. And what he says is, based on his extensive study of the subject, and here he is showing it in Japan, but he got the same results for Japan as he did for the United States, all the Western countries. And the point was that the tight correlate to increasing obesity and diabetes was increased intake of omega-6 cooking oils rather than saturated fat, which is like saying animal fat, and to a large extent total fat. And he also said it didn't that precisely correlate with sugar. The word sugar, though, is a little confusing because sugar could mean glucose, like what's in starch. Sugar could mean table sugar, sucrose, which is a combination of glucose and fructose 50-50, or it can mean high fructose corn syrup. High fructose corn syrup is often 65% fructose, okay? And that's much more prone to causing fatty liver, diabetes, and weight gain. But still, this is pretty impressive that omega-6 cooking oils were the tightest correlate with increasing obesity. But what I'm trying to say is a lot of times there's a tendency by speakers to just say it's because of omega-6 cooking oils, one thing, but it's multiple things. There's also across this time course, especially since 1970, there's been a big increase in glutamate in the food, not just MSG, but glutamate in general. I'll talk about that briefly in a little bit. There's been a big increase in high fructose corn syrup. There's been a big increase in glyphosate. And there's been a big increase in endocrine disrupting chemicals, especially those estrogenic chemicals, which are fat storage hormones. So it is multifactorial, but all of these things are avoidable once you understand them. Okay, and then now, the way the food companies, they've gotten smart. They got big budgets. They do research. Well, they'll check multiple things to optimize the taste of their food. For example, they call it the bliss point to get just the right amount of sugar, salt, and fat, and also glutamate. Okay, and this guy, Michael Moss, wrote a book about this called Salt, Sugar, and Fat. And they'll also, they'll adjust the texture of it for ideal mouthfeel. And people will be addicted. This is why you hear about Lay's potato chips. I bet you can't just eat one. Okay, so people become addicted to stuff. And what they should realize is they're being addicted because of the chemicals in there. It's like a drug, not because it's intrinsically a good food. Okay, a little bit about how a neuron works. So here's a brain cell, a neuron. Here's the cell body, and you're going to have the nucleus in here where the DNA is. These are some mitochondria to make energy, ATP. Dendrites are the incoming sensory signals. Information comes in. When the neuron is activated, it fires an action potential, begins right here at the axon hillock, and it'll travel down the axon, this long tubular part of the neuron, and it'll reach the synaptic terminal. At the synaptic terminal, as the action potential arises, it will open up. It causes a change in voltage, so it opens up the voltage-gated calcium channel. You actually need to know this, voltage-gated calcium channel. That allows calcium to come into the cytoplasm of the cell, and it will then cause these neurotransmitters. NT is for neurotransmitter. These vesicles will travel to the synaptic cleft, the plasma membrane right here, and they will release this neurotransmitter into the synaptic cleft. It'll diffuse across to the postsynaptic neuron and cause its activation, okay? And that will, exert an effect on the postsynaptic neuron. And the most common, over 90% of the neurotransmitter in the brain are glutamate, and it is an excitatory neurotransmitter, so it will activate the postsynaptic neuron. So that's important to know. Glutamate goes across the synapse, activates the postsynaptic neuron. All right, so now here's what I want to talk about. Everybody's heard of MSG and only wrote about this in the 1960s. And what MSG just means, it's the monosodium, single sodium salt of glutamate. Glutamate's an amino acid. There's 20 amino acids. And it turns out everybody thought, oh, they're just addicted to MSG. MSG tastes good. And the way it works is our taste buds are for sweets, but there's also a taste bud for amino acid, for glutamate. It's also called the umami taste receptor. And the point of this is our ancestors worried about starving to death. So if they found something that was a protein source, they would get released to reward neurotransmitters in their brain for recognizing the glutamate and say, this is good, eat more of that. That might save you from starvation. Okay, so the relevance, though, is what the companies have figured out. First of all, they realized the public doesn't want anything with the word MSG in it. So they started putting it under different names like hydrolysis, extract, isolated protein, isolated soy protein, isolated vegetable protein, barley malt extract. Okay, but what I'm getting at is now what they found out is all they have to do is process this protein more and break up its individual amino acids. So a regular protein that's intact has a whole string of amino acid connected by peptide bonds. And there's some proteins that have a lot of glutamate, like gluten, the bread protein, wheat protein, casein in milk, soy, whey protein also from milk. But if they process it a lot, like let's say the milk, they ultra pasteurize it, remove the fat, they can do additional procedures to it. These glutamates get all separated and they become free, meaning they're no longer bound to each other. And the relevance is the more free glutamate hits your mouth as a bolus, that means in one fell swoop, not connected to anything else, the more of a reward neurotransmitter effect it gets, the more likely you are to become addicted to that food. So that's why, and it's typically described as being MFG, manufactured free glutamate. But the problem is this, some of this can have an excitatory effect on your brain, and that's not good. It can overwhelm the body's capacity to handle glutamate when it comes in so rapidly as a bolus. Okay, this can make people addicted to foods. There was a lady who wrote a good book about this, Catherine Reed, on how to make manufactured free glutamate. Her book was about her daughter who had autism. And when she removed all the MFG from the child's diet, the child got better. She had a moderate severity of autism. The mother is a PhD biochemist who specializes in protein. So she sort of had the perfect background for understanding the issues with because this is a protein. I mean, this is an amino acid. So she figured it out. Her book's called Fat, Stressed, and Sick. She also has online videos. They're good. She's a smart lady. Okay, normal insulin sensitivity. So insulin typically will bind to the receptor on the plasma membrane of a cell, let's say a skeletal muscle cell. That's where a lot of glucose goes after you eat a meal. After eating a meal is called postprandial. So insulin binds to the receptor, and it's the insulin itself was released by the pancreas in response to elevated glucose from the meal. And so it goes to the skeletal muscle, causes the glucose type 4 transporters to merge with the plasma membrane, and they form like an ion. They form a channel for the glucose to come right into the cell. Otherwise, the glucose can't get into the cell. And that's what you want. You want the glucose to come in the cell. The skeletal muscle can store it as glycogen. All right. And here's how the cell normally makes energy. This is the mitochondria here. This is the outer mitochondrial membrane, OMM, inner mitochondrial membrane, IMM. These are the protein complexes in the inner mitochondrial membrane, complex 1, 2, 3, 4, and then complex 5 is ATP synthase. That makes ATP the energy currency of a cell. It's like a $20 bill in a cell. By the way, oxygen is the ultimate electron acceptor. You're going to hand down electrons, as E- is an electron, like a fireman bucket brigade, to progressively stronger grabbers of electrons. That means they have higher electronegativity, a measurement of how much a molecule wants to grab electrons. So oxygen has a tremendous desire to grab electrons, okay? And they use the energy of passing along these electrons to pump protons. H plus is a proton. So in a sense, they've split the atom here. They've split the hydrogen into its positively charged component, H plus, and its negatively charged component, an electron from its outer orbital. Okay, so the electron is passed down here, and then the hydrogen is pumped into this space between the outer and the inner mitochondrial membranes. This is called the intramembranous space. And you build up a proton gradient there, and it's extraordinarily high, negative 160 millivolts, okay? It's like the highest gradient in the human body. Okay, well, the point of all this is when you eat excessive amounts of dietary fat, especially saturated fat, it will inhibit electron transport at this level. And this is from the Michael Brownlee paper, the best paper ever written on dialysis by Michael Brownlee in 2004. He won the Banting Award. It's called Unifying Theory of Diabetic Complications. You can get the paper for free if you go to ADA.org, American Diabetic Association.org. If you go to PubMed, you just get like an abstract. You won't even get an abstract. You get nothing. If you're willing to sign in and give your email to ada.org, they'll let you watch Michael Brownlee's lecture on it. It's a masterpiece paper. It's an AO, academic orgasm paper. Okay, it's so beautiful. Anyways, but once this is blocked, you now get a backup of electron transport, a backup of Krebs cycle, and a backup of cytoplasm reactions in glycolysis. And it causes all kinds of negative secondary reactions that you really don't want happening. Okay, so another thing is this is sensed as what has been called overnutrition. The cell basically says, we've got too much energy in here to process for our metabolism, so we can't allow any more to come in. We don't want any more glucose coming into the cell. So it will block the movement. Insulin binds here, and instead of these glucose type 4 transporters going up to the plasma membrane, they won't go because they're blocked by this overnutrition signal. Glucose type 4 is just a type of glucose membrane transporter that is insulin dependent, because there's other ones that aren't. So you need to know that. Glucose type 4 transporters are insulin dependent, all right? So when the skeletal muscle can't take up the glucose after eating in the postprandial phase, then the glucose accumulates in the blood. So you get high blood glucose, hyperglycemia. So this is postprandial hyperglycemia. All right, and chronic postprandial hyperglycemia from chronically eating these high-fat meals leads to more and more glucose in the blood. Some of it goes to the liver, and it ends up being stored because there's too much of it as fat, and you start getting a fatty liver. having accumulation of fat in the liver leads to the liver becoming unable to manage blood glucose. The main job of the liver is to make sure your brain has enough glucose. That's the liver's job, especially during the fasting phase. It'll break down glycogen, which is a stored polymer of glucose, or it'll run gluconeogenesis, a reaction to make new glucose, to make sure the brain has enough glucose. Okay, it's important to know that's the most important thing the liver does. So if the liver starts becoming unable to accurately regulate blood glucose, has to sense the level correctly, it'll keep on releasing too much glucose into the blood. And now you will have hyperglycemia during fasting. So you have a fasting blood glucose over 126, for example. All right. And this can be called glucose overnutrition. And the relevance is there's some cells in the body which do not have glucose type transporters, okay? They will simply take up glucose in proportion to whatever its blood level is. And when it's chronically elevated all around the clock, 24/7, it will damage those cells. It'll damage endothelial cells because they don't have glucose type 4. They just keep taking up glucose and they're overwhelmed by it. In a sense, the same thing that happened with the SAT fat and the skeletal muscle can happen to them. It can cause dysfunction of the mitochondria, backup of their metabolic reactions, and all these secondary side effects. Same thing happens in the eyes, diabetic retinopathy, in the kidneys, diabetic nephropathy, and they get that endotheliitis, you can call it diabetic microvasculopathy in the foot, and they get lots of amputations. The diabetic is screwed in the foot because you can't put an angioplasty balloon down here. There's no outflow vessel to bypass to. So they get, any Western hospital, there's a bunch of diabetics getting their toes or their feet amputated every day. And eventually they get their lower leg amputated, even their upper leg amputated. In my career, I've seen many, 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 many thousands of those. Okay. Now here's a key thing to know about diabetes. One of the most important things you can know is they wanted to try to figure out, how the fat is getting into the cell. And so they blocked the plasma membrane protein transporters of fat, like CD36. But what they found is that the fatty acids were still getting into the cell, even when they blocked the protein transporters. And they came to the conclusion, this is the paper here by Anthony J. James Hamilton, here's a reference up here, that the fat was able to just intercalate into the outer leaflet of the plasma membrane. It can become protonated and then, drop its charge, become less polar, and it will then flip-flop into the inner leaflet of the plasma membrane and then move into the cytoplasm of the skeletal muscle. So the bottom line was this: they couldn't control it with a drug. The only way to decrease the amount of fat that was getting in the skeletal muscle was to reduce the amount of dietary fat. So this is another reason that I'm a big believer you want to eat low fat. And they've shown it in multiple studies going back to the 1920s, the Shirley Sweeney paper, Hemsworth paper, Rabinowitz paper, and there's a whole bunch of other ones. When people lower dietary fat, they increase insulin sensitivity, and type 2 diabetes can be reversed if they still got, an intact pancreas insulin production, which they should for years, typically. Okay, this is just showing a little bit more about how, abnormal high amounts of dietary fat will damage the arterial lining. They'll cause hypoxia of this endothelial line. So a lot of things are happening simultaneously. The high fat's causing insulin resistance, so you're ending up with hyperglycemia, which damages these endothelial cells, but it's also causing some tissue hypoxia. Actually, Roy Swank, the neurologist, and he did some work with Dr. McDougall as well later in his career, he spent a long time studying arteries, and he came to the conclusion that he felt the hypoxia induced by the high-fat meals was injuring the arterial endothelial cells, and that was contributing to opening up blood-brain barrier permeability, which is increasing the risk of multiple sclerosis. And other things are happening here. You also, when you injure the arterial lining cells, you get an increase in the amount of beta amyloid. Beta amyloid is both present in the extracranial part of the body and inside the brain. So you get more beta amyloid protein from the periphery of the body moving into the brain, and you have less being pumped out. So negative here is for the pumper beta amyloid protein, less being pumped out of the brain. You also will get decreased amount of these glucose type 1 transporters across your endothelial cells. These are not insulin dependent. What this means is you get less glucose going into your brain. So this is all bad. You're getting more beta amyloid protein in your brain. You're getting less glucose that your brain cells burn through tons of glucose. If you ever look at a PET scan, that's like a fluorodeoxyglucose scan of the brain for cancer patients, and just look at one of them in the brain. Tons and tons of glucose uptake in the brain. It's the hungriest, most metabolically active part of the whole body. The only thing that's comparable is the left ventricle, which is pumping all the time. I can tell you it's the hottest thing on a PET scan because the brain uses tons and tons of glucose. That's all. The reason they do a PET scan is because cancer also uses a lot of glucose once it's cancerous. That's a different topic. We're not going to get into that today, but I'm just saying the brain wants glucose, lots of it. All right, one brief thing on leaky gut. So your normal gut is called the enteric tract. The gut lining cells are called enterocytes. between them, they have these TJs for tight junctions. Fiber feeds the good gut bacteria. There's really only two types of gut bacteria that are worth knowing about. There's a good gut bacteria and there's a bad gut bacteria. The good bacteria are fed by fiber. They make short-chain fatty acids here, SCFA. The most important one is butyrate. The butyrate goes to the enterocytes. They use it to make tight junctions. That's what you need to know. So if they get fiber, they're probably going to be okay. But if you eat a diet very low in fiber, then they have a hard time making these tight junctions, and you're greatly predisposed to having leaky gut, whereby bacteria, bacterial endotoxins are much more likely to get across the gut lining and get into your lamina propria, deep to the gut lining cells, and cause problems. In addition, you can get larger chunks of protein. Normally, there should be nothing more than 3 amino acids attached to each other, tripeptide. So you can have an isolated amino acid, 2 of them is a dipeptide, 3 of them is a tripeptide, but you can get much bigger pieces of protein across these open spaces when you don't have intact tight junctions. And that can lead to, molecular mimicry, autoantibodies with cross-reactivity, all that stuff, autoimmune disease. But the reason I'm mentioning it in this context related to the brain is whenever the gut barrier is opened up, you got leaky gut, that usually means you also have leaky blood-brain barrier. So it's bad. Okay, when you get a stroke, what causes opening of the blood-brain barrier will also cause leaky gut typically. Traumatic brain injury will also cause some leaky gut. And here's a list of all the things that can cause leaky gut, like antibiotics, killing off the good gut bacteria, for example. Vegetable oils are prone to doing that. Diets with low in I'm not going to go through all of them, but the point I'm saying is if I had an autoimmune disease or I was hypercoagulable and wanted to decrease my predisposition to forming unwanted blood clots, I'd go through this whole list and avoid all those things. Okay, here's just an example of how it'll happen. If you got leaky gut, the gram-negative bacteria, their LPS, lipopolysaccharide, also called their endotoxin, can get across into the blood. Gram-positive have an analogous thing called LTA, lipoteichoic acid. And these will be predisposing the blood to be more coagulopathic, more likely to form clots, prothrombotic. And the fibrinogen proteins, which normally are cylindrical, that's called an alpha helix configuration in secondary protein structure. So alpha helix cylindrical, they look like a slinky, the thing that goes down the stairs. It will then change. Instead of becoming cylindrical, it'll become flat. And this is called beta sheet configuration. And now they can stack up on each other and they'll form these aggressive blood clots. So a normal blood clot kind of looks like a bunch of pieces of spaghettis, and the body can dissolve it real easily when it needs to. But when you get these abnormal clots because of bacterial endotoxin, they kind of look like dense matted deposits. You can imagine like a bunch of knots tied in the spaghetti, and it's hard for the body to dissolve those. You can also get those from infections. And this is called amyloidogenic clotting or amyloid clotting. The big researchers on this was Douglas Kell from England and Etheresia Pretorius from South Africa. They deserve to win a Nobel Prize for their work. It was fantastic. And they got tons and tons of citations for all their research papers. They wrote a great paper called Iron Behaving Badly. You go watch videos of either one of them on the internet. They'll have talks about all this stuff, amyloidogenic clotting, amyloid clotting. So the bottom line is leaky guts, not just a problem for, having gut irritation, irritable bowel syndrome, ulcerative colitis, and Crohn's disease. It's also a problem for autoimmune disease, but it's also a problem for coronary artery disease and for dementia because it's plugging up your arteries. The main thing that gives people, disease is plugged up arteries. TBI doesn't just mean traumatic brain injury, total body ischemia. It's happening in your brain, in your spine, everywhere. Okay, so here is the blood-brain barrier, BBB, and here's the glucose type 1 transporters. Those are ones that are not dependent on insulin. They will let glucose come across here, and then it'll go to your brain cells. Your brain cells need that glucose. They've got glucose type 3 transporters. They're not insulin dependent, but they also got glucose type 4 transporters that are insulin dependent. And this is a big deal because all the textbooks, they don't know this. This is not in any of the regular textbooks. You might not even be able to find this in neurology textbooks, but you will find it in the research papers. So the relevance is insulin resistance in the periphery also causes insulin resistance in the brain. And these neurons cannot get enough glucose, especially in times of urgency, severe exertion or intense stress. So they can be damaged by that. They can go into apoptosis. When a neuron can't meet its metabolic demands, it doesn't have enough energy producing capacity, the neuron can die, go into apoptosis. So this is an important thing to know. There's glucose type 4 transporters in your hippocampal neurons. There's glucose type 4 transporters in your substantia nigra, the neurons related to Parkinson's disease in the midbrain there. Okay, now here's the thing too. A lot of times everything's fine. You're just taking it easy, but you could be walking down a path in a forest and then, here come 3 coyotes at you. What do I do? Should I stand my ground? Should I climb a tree? What am I going to do? So you have to very quickly go from 0 to 60 miles per hour. And the brain has a way to do that. There's endoplasmic reticulum is a calcium reservoir, stores calcium inside the cell. and it has connection points with the mitochondria. They're called MAMs, mitochondrial-associated membranes. And so when you need a sudden increase in activity, you got to get that neuron going real fast. It has to produce tons more ATP than it was doing at rest. They will push calcium into the mitochondrial matrix, and that will cause upregulation, meaning increased production and activity in the enzymes of Krebs cycle. And this can then get this neuron to generate ATP very quickly. But the problem is that if this same neuron has insulin resistance due to these chronic high-fat diets and the other things that contribute to insulin resistance, then the glucose can't get into the cell. But evolutionarily, this didn't happen to our ancestors such that they'll send too much calcium into this mitochondria because they're like, hey, where's the glucose? They're not waiting for this because they just expect it to work. And the net result is this excess amount of calcium can be deposited in the mitochondria and cause the mitochondria to die, and then the entire cell can die from that. If you lose too many mitochondria, the cell will just die. It'll go into apoptosis. So this is another reason why diabetics tend to be very cognitive impaired. The most cognitive impaired patients I ever talk to in typical big groups will be number one, the kidney failure patients. Okay. Number two, obstructive sleep apnea patients. Number three, these diabetics. Most of them are cognitively impaired. I can tell you my internal medicine friends and my personal experience too, most of the people I see over 60 are cognitively impaired. They can say hi, yes, a lot of them, most of them, but they can't, they're sort of become kind of cow-like. They're not capable of quick, interactive conversation or thinking, like a healthy person is. Okay, this is just a picture of the book there. So here's a little bit on fructose. And it's especially high fructose corn syrup. Fruits, again, I think are good. Fruits are different than high fructose corn syrup. Fruits have fiber, okay, which slows down absorption. Fruits have relatively little fructose, only about 5 grams per serving. Fruits have a lot of potassium, magnesium, vasodilators, okay, that keeps arteries open. That's important. And they also have antioxidants like vitamin C, for example, which increases uric acid excretion from the body. All right, but the key difference is glucose, when it comes in the cell, like let's say from starch, it goes all over the body. Some of it comes into the liver. The liver is great in handling glucose. It's fantastic. It's the expert at handling glucose. It only runs glucose through glycolysis to produce energy if it needs to. And there's a regulatory enzyme here called PFK, phosphofructokinase, that is very tightly regulated. Okay, but the relevance is that fructose is different. When somebody guzzles down, some energy drink full of high fructose corn syrup, the fructose, almost all of it, instead of going all over the body, it goes right to the liver through the portal vein. It gets phosphorylated, and the byproduct of that ATP that was used to phosphorylate it leads to uric acid production. That's important. Because this is not regulated, it can happen very rapidly, and you can accumulate a lot of uric acid here. The next thing is that the fructose doesn't enter the beginning of glycolysis. This is the 6-carbon phase. Both fructose and glucose are both 6-carbon sugars. And because it enters at the 3-carbon phase, it bypasses all the regulatory steps. And what this means is fructose can very rapidly come in as a bolus, and then it runs to the end of glycolysis, and the liver's like, where did this come from? I don't have anything. I don't need this to happen. And so it just takes the byproduct of that, like a 2-carbon molecule here, acetyl-CoA, the acetyl groups I'm referring to, and it'll just make them into fat. So it predisposes a person to developing a fatty liver. Also, the glyphosate, it's thought, according to Stephanie Seneff in particular, their research, that it's a strong predisposer to fatty liver. Fatty liver is like prediabetes, diabetes of the liver. Okay, when the liver's fatty, it's less able to regulate blood glucose. Okay. So here's the next step. The uric acid goes into the blood, and it's a bridging molecule sticking RBCs together. So the blood thickness, viscosity goes up. You're predisposed to hypertension. It also causes some activation of SAN, sympathetic autonomic nervous system, meaning that it has a bit of a stress effect. It inhibits endothelial nitric oxide. And you need that nitric oxide production vasodilator to work in conjunction with insulin, because when insulin enters the skeletal muscle after eating a meal, you have to open up those capillaries so they can get contact with the skeletal muscle cells. If you inhibit the nitric oxide from opening up those capillaries, the insulin can't get to the muscle, so that causes insulin resistance. Does that make sense? If the insulin cannot get to the skeletal muscle because all the capillaries are blocked, vasoconstricted at rest, then you get insulin resistance because you can't get an insulin effect, and that's going to cause increased blood glucose. So it has insulin resistance effect contributing to diabetes. It also activates platelets, making them more prone to clotting. That's bad. Also, you have an enzyme in the blood called insulin-degrading enzyme, and it removes insulin. But if the levels of insulin are chronically elevated due to insulin resistance, this insulin-degrading enzyme can only be made in limited quantities, and it has higher affinity for the insulin than it does for the beta amyloid protein. This means that you're going to get increased beta amyloid protein in the blood and subsequently increased beta amyloid protein in the brain. So this is also part of how it contributes to cognitive impairment. The next point is that some of the fructose does actually stay outside the liver, and it causes increased sodium, salt absorption in the gut. It causes increased sodium retention by the kidneys. So the kidneys don't void out, pee out as much sodium. That also contributes to hypertension. So you can see all the things happening here: worsening hypertension, worsening diabetes, increased accumulation of beta amyloid. So this can contribute to increased risk of dementia, cognitive decline, neuronal injury. Okay. But like I said, too, it's a special circumstance there. You know, a lot of this high fructose corn syrup stuff that also often has Hg in it, mercury in it, because it's a contaminant. As you produce high fructose corn syrup, it gets often filtered through chloralkali vats, and that can be a complication. They used to advertise high fructose corn syrup as a preservative, but it was really because of the mercury effect. Okay, now this illustration is related to the work of Roy Taylor. What he found is in people with diabetes less than 4 years, type 2 diabetes, they would have fatty livers, and if they could lose weight, like let's say 30 pounds, the fat would be first taken out of the liver. And once they lost the fat from the liver could now accurately manage blood glucose. And so their diabetes was cured. So that's the point. Typical diabetic, they go on a keto diet, they don't ever get cured. They just progressively get worse and worse, and they go on a bunch of pills. Versus if they can lose the weight, they're routinely cured, type 2 diabetes. So as long as that's what it really is, type 2, and that's what it usually is, they can cure it. If they've lost a bunch of their pancreatic beta cells for other reasons, because they're eating too much fried food, too much aluminum, then they might not, then they don't have the adequate insulin production. So they can be, they often call 1.5 diabetics, somewhere halfway between type 2 and type 1, you know, like the child onset it's typically used to be called. So this is just, you know, Roy Taylor concept again, that once they lost the weight, their blood glucose is normalized and they were cured. Okay, so how you lose the weight? The best way is low fat, low sodium vegan, but you know, you can lose the weight anyway. You could fast, you could, you know, eat some special meals or whatever, but eventually, you know, you got to eat on a routine basis. So you might as well eat something that's healthy and good for you and keeps you thin. All right, here's how a regular cell does its work. You have a potassium sodium ATPase pump. It takes in 2 potassium for every 3 sodiums pumped out. And in so doing, you're going to lower the amount of sodium inside the cell relative to outside the cell. So typically outside the cell, you got about 140. Na means natrium. That's a Latin word for sodium. Okay, inside the cell, you got 14. So you have 10 times more outside the cell than inside the cell. That's a chemical gradient. In addition, you have a negative charge inside the cell along the plasma membrane. It's about negative 65, negative 70 millivolts. And the relevance is that a positively charged sodium ion means positively charged molecule or element, it wants to come into the cell. The sodium wants to come into the cell to equalize its concentration gradient, okay, of 10 to 1. And it also wants to come in the cell because it has a positive charge, and the inside of the cell is negatively charged, negative 65 millivolts. So in a sense, separating charge across a surface like this and then having current flow through the ion, that's a battery. That's how a battery works. So the cell knows how to make electrical energy, and it uses almost 2/3 of its energy. A neuron does 50% to 2/3 to run these pumps, because everything in the cell, as far as the work done by the plasma membrane, depends on them. Okay, and the big thing that has to be managed is calcium. When calcium comes up in a cell, they joke like the Lord of the Rings, one ring to rule them all. It turns the cell on. So in a sense, you could think of potassium and sodium as minimum wage workers, and calcium as the big aristocrat that comes in and makes the cell do whatever it's supposed to do. So in a typical neuron, that would be to release its neurotransmitter, which is usually going to be GLU, is the abbreviation for glutamate. Okay, and the relevance here is that you can see there's a high concentration of calcium outside the cell. It's about 15,000 times lower inside the cell. In order to pump against that gradient, like here's a knockout exchanger, this is coupled to the sodium gradient, and this can pump calcium out of the cell. It uses the gradient produced by this, so it's still energy dependent. So that means it's active transport. And you always are going to need ATP. You always need ATP. You need to know this. This is going to be important. You have to have ATP because you're going to need that energy to generate these gradients so you can pump calcium out of the cytoplasm. And you have to pump calcium out of the cytoplasm. If you don't pump calcium out, this glutamate will keep on releasing more and more glutamate, and it will exhaust the post-synaptic cell. It'll be overexcited, and that can cause it to die because it won't be able to meet its energy demands. Okay, here's a little bit more, same thing, but a little more detail here. There's also something called the endoplasmic reticulum. The S just stands for sarcoplasm, and that's only relevant to muscle. In a neuron, it's just ER, endoplasmic reticulum. And this is the calcium ATPase, so an ATP-dependent pump to pump calcium out of the cytoplasm and get it in here for storage, okay? So that takes ATP. There's also a plasma membrane calcium ATPase that also uses ATP. The key point here is this pump is related to ATP, this pump's related to ATP, this pump's related to ATP, meaning that the mitochondria has to make ATP in order to effectively be able to get calcium out of the cytoplasm. You need to know that. Tons of things depend on that because calcium activates the cell. And this circa, it's called the circa pump, to pump it into the endoplasmic reticulum, it also needs ATP. And there's a lot of things that inhibit this pump. So you need to know that too. That's going to become relevant. So if you don't have the ability to pump calcium outside of the cell is going to keep on being overactivated, and that's going to lead to cell death. And whatever the cell does, calcium activates. If it's a skeletal muscle, it contracts. If it's a vascular smooth muscle, it'll contract. Cardiac muscle, it'll contract when you get increased cytoplasm calcium. Other cells that are designed for releasing hormones, they'll release their hormone when you get increased cytoplasm calcium. It's sort of like a universal activation signal for a cell to do whatever that cell does. Okay. Now, to make a little bit more detail here, when glutamate comes and binds to a cell, so this will be a postsynaptic neuron, it will activate what's called the AMPA receptor, letting sodium come into the cell. That'll increase the positivity of the charge in the cell. Once it becomes more positive, there's typically a magnesium that was hiding in here. It's kind of off this chart. These images didn't transfer fully when I sent them from one computer to another. But anyways, magnesium will bounce out of the center of the NMDA channel, and that will allow calcium to come into the cell, and it'll raise calcium. So glutamate, the neurotransmitter, causes increased calcium in the cell. By the way, glyphosate can activate the glycine component of this receptor and also increase the amount of calcium getting into the cell. If you have a magnesium deficiency because you don't need enough plants, magnesium is right in the center of chlorophyll, that can increase the activity of this receptor because it'll tend to have a shortage of magnesium, meaning the channel's open for calcium to enter. You don't want that. There's more to it than that, but that's the money, what we just covered. Okay, so here's just an example of excitotoxicity. Let's say this cell is overactivated for whatever the reason. The glutamate then is released in excessive amounts, goes to the postsynaptic neuron. It overactivates this postsynaptic neuron, opening up the calcium channel here, like the NMDA receptor. You'll get elevated cytoplasm calcium in the postsynaptic neuron, and you can activate this neuron here called calpain. So it's a perfect name for this enzyme. It's a protease, meaning that it chops up proteins. Calcium activated, pain, it has painful consequences. So when calpain gets activated, it'll start to damage proteins, including the NCX, with the knockout exchanger. That's the calcium pump. So you create a vicious cycle because you can't pump calcium out of the cell effectively when you damage that, and the cell will progressively become overactivated and it'll die. Excitotoxicity. Okay. So this is important to know because there's a lot of things that are going to increase glutamate transmission, and there's other things that are going to decrease the ability of the cell either to make ATP or to pump calcium into the endoplasmic reticulum. All of those things are going to increase the risk of neuronal cell death. Okay, ways to avoid it. I'll give you a better slide in a moment here. This is just an old slide I had. You know, you eat your plants, you get your potassium and your magnesium. You need that potassium to run the pumps. Normally, our ancestors probably ate 25 times as much potassium as sodium. Okay, but nowadays, the modern American typically eats about 10 times as much sodium as potassium, and that makes it difficult to get the ion balance correct across those neuronal plasma membranes. Okay, they'll tend to dissipate that sodium gradient and have less ability then to pump the calciums out. You'll get magnesium in the center of chlorophyll, so you get the magnesium. You need that for run all your ATP-related reactions, and it's also a vasodilator, and it also blocks the center of the glutamate receptor, the NMDA-type glutamate receptor. Low-fat diets are beneficial. You'll avoid rouleau formation. You'll avoid hypertension. You avoid insulin resistance, so you avoid tissue hypoxia. You want to avoid excessive dietary sodium. Caffeine is bad, just like sleep deprivation, excessive psychological stress, because it increases glutamate transmission across the plasma membrane there, because it elevates cortisol. Same thing as stress. Alcohol is directly toxic to neurons, and it's complex, some of its other aspects. I'm not going to get into that. Tobacco is a stimulant, so it's going to increase the metabolic rate of the neuron. I'll talk about that a little later. Excessive stress. It's important to sleep. You really help your neurons when you sleep. You want to filter your water. There's a lot of chemicals in the water that are toxic to your brain, especially aluminum, fluoride, and also these endocrine disrupting chemicals. They've done some work on these, including this guy, Gilles Sertolini. And what they found was that they're not just endocrine disrupting chemicals, estrogenic. Most of them, about 80% of them, have a neurotoxic effect as well. Okay, exercise is great for the brain. You want to make sure you're in the habit of routinely exercising. Most things that smell bad, our brain is sort of like better designed than we realize. If something smells bad, it's probably bad for you. Paints, glues, air pollution, exhaust, all those, avoid those things as best you can, because quite often they end up being circa inhibitors. Okay, the next thing is avoid processed food, lots of toxic chemicals in there. You're better off eating organic food only, even though, organic's not perfect, if you have a choice. I mean, it's good to eat your plant foods too, but I'm saying if you have a choice, organic is preferable. You avoid the atrazine on the corn. You avoid the glyphosate. That's sprayed, of course, especially on soy, but it's also sprayed on non-organic beans, for example. Avoid unnecessary drugs. Well, they all got side effects. You don't take it unless you need to. So here's something I thought was interesting. This is a mitochondria. And I knew there were issues with mitochondrial toxicity, but I couldn't find any in my books. I went through all my biochemistry books. I own about 5 of them. I went through my neurology textbooks. I couldn't find anything about mitochondrial inhibitors. So then I started going to the research papers on the internet, and I quickly found over 50 of them. And there are a lot of these things are common. Statin medications can have a detrimental effect on coenzyme Q of your mitochondria, intermitochondrial electron transport. Not good. Tylenol can affect complex 3. Okay. Common medications like serotonin selective reuptake inhibitors for treatment of depression. Those can inhibit mitochondrial electron transport. The relevance of this is anything that's diminishing the mitochondrial ability to make ATP is also diminishing the ability to keep up with pumping calcium out of the cell. And you remember the metaphor of the camel, the last straw that broke the camel's back. All of these things are adding up. People's health is being nickeled and dimed into the ground. Okay. Metformin, a very common medicine for, treatment of prediabetes, sort of like a mild diabetes. All right. Not good. Okay. It's inhibiting complex 1 of mitochondria. And why do I think that's a bad thing? Because I've had doctors ask me, do you think I should take metformin to increase longevity? I'm like, yeah, you want to inhibit your mitochondria? Stupid. All right. Haldol, for example, the antipsychotic for treating schizophrenics, an acute psychotic episode with schizophrenia, for example. It inhibits complex 1. And guess what? It secondarily, over time, leads to Parkinson's disease. Well, I think that's something to be concerned about because you can get a slower onset drug-induced Parkinsonism from serotonin selective reuptake inhibitors, antidepressants. Okay. And I wonder if metformin, eventually will be related to that. Lasix, a very common diuretic, can do that. PCB is a common estrogenic pollutant, can do that. Trichloroethylenes, that's like used in dry cleaning, liquid paper, degreasing chemicals. That also can inhibit complex 1 and potentially down the road lead to Parkinson's disease. Neurologists are well aware of this. They call it TCE, trichloroethylene. All right. So I would not want to take a drug that might lead to Parkinson's, that lowers my energy production in my brain. Okay. Chromium can potentially do that. Mercury, Hg, can potentially do that. All right. There's all papers on all this stuff. A lot of people, like typical patients, they go for procedures, say, I want to be knocked out. I don't want to feel anything. I'm the opposite. I try to avoid having a medical procedure, but if I have to go for one, like my mom died of colon cancer. Okay. So I went and got a colonoscopy. They go, do you want to be sedated? I said, no, I'll be fine. I had no sedation. I was just fine. I got teased about that, but you know what? I came out of it fine. I don't want those benzodiazepines, blocking my memory. What if it doesn't come back like it did before? I worry about that. So here's an example. Propofol inhibits complex 2. That would concern me. Okay. Let's see. A lot of antifungals will inhibit complex 2, for example. They put antifungals in tons of personal care products, and they put it on foods a lot of times too, because they don't want mold growing on it, or then they can't sell it. Okay, titanium dioxide nanoparticles, that can do it as well. That's in a lot of things, like a whitener in a lot of pills. It can be a whitener in other things as well, for processed products. Flame retardants, like I won't wear my surgical blue gown if I don't have to. If I'm just doing something that doesn't require it, I won't wear that. I'll just wear some other barrier protector rather than wear that. If I'm doing something like minor procedures, suture removal, whatever. Okay, F- in the water inhibits complex 4, fluoride. Okay, PFOAs from nonstick cookware can inhibit the cytochrome C. Okay, lead. Some things will concentrate lead. Okay, there's, some teas will do that, for example. That's one reason why you might want to avoid them. Okay, and you see how each one might only have a small inhibitory effect, but it all adds up. Fluoroquinolones are used because they'll cross the blood-brain barrier. Remember that whenever you hear fluoride, quite often that's added to a drug because it increases the ability to cross the blood-brain barrier. So quinolone antibiotic, you add a fluoro to it, fluoroquinolone. Now you get increased crossing the blood-brain barrier. So it's used to treat brain infections. It's used to treat testicular infections, ovarian infections, because it can cross the blood-testicular barrier. All right. Beta-lactam, common penicillin-related antibiotic. Aminoglycosides, a common antibiotic. These can all inhibit mitochondria. Okay, this can all add up. Alcohol inhibits related enzymes in Krebs cycle. So does arsenic. Traumatic brain injury does as well. Silver does. So you can see these are common things, and there's plenty more of them that we just don't need to go into all of them. But so this concept of the last straw that broke the camel's back is important. And this is why I think you should try to avoid everything you know of that you can that's harmful to your health. Because what you should really strive for is what's the best I can be? What's the best I can do? Because in my experience, lots of people, they say, well, I'm doing pretty good. I'm aging better than most people. I'm not as fat as my cousin. And if your goal in life is to just not be as fat as your cousin, you'll probably be a little healthier than your cousin, but you'll still, maybe die 2 years later, 5 years later. Why not be the best you can be with your health? Because in the process of trying to optimize everything, you'll learn a lot and you'll keep on improving. The older we get, the more fragile we get. So the more we have to be careful about our health habits in order to stay optimally healthy. And like I said here, this is just all the things that are all stacking up. If you don't eat plant foods, you're going to be low in fiber. These are the most common nutrient deficiencies. You're low in fiber, potassium and magnesium, your vasodilators, your nitrates, vasodilator, also your antioxidants, okay? You have to have a good social attitude that helps you to manage your stress, having a sense of purpose in life, etc. will help you. Get your sleep, manage your stress, avoid meds that you don't need. Like I said, a lot of these medications, I showed them on that last mitochondrial inhibitor slide, are toxic. Aspartame is kind of like glutamate. It's an excitatory amino acid, aspartate, and that can cause overactivation in neurons. All this stuff adds up, and I showed some of these chemicals on that last slide. So the point I wanted to make is avoid all these chemicals as best you can. That's why you want to learn about this, and it's pretty easy to learn. And once you're aware of it, you avoid these things. And it's good to be a minimalist. Okay, now here I'm going to explain to you my theory, the Peter Rogers MD theory of dementia. So basically, you normally have neurovascular coupling. That means you'll have a baseline metabolic rate in your neuron. Can you guys see my hands? Okay, so
you're very small in my screen. Yeah, you're not big, but
okay, fair enough. I'll show my hands now, and then I'll show the slide. It'll make sense. So here's the metabolic rate of the neuron, and here's the oxygen and glucose delivery. I jokingly called it GOD for glucose oxygen delivery, okay? So normally they should be coupled. That's called neurovascular coupling. Now, if you drop the glucose and oxygen delivery, because the high-fat meal drops oxygen and glucose delivery about 15 to 20%, you have sodium vasoconstriction. That makes it worse. And then you could have baseline atherosclerosis, baseline, thickening of the wall due to diabetes and hypertension. All of those things are lowering the oxygen and glucose delivery to these neurons. Okay, you superimpose atrial fibrillation, congestive heart failure, aortic regurgitation, the valve, aortic stenosis. You're going to drop the ability to deliver oxygen and glucose to this neuron. You can also have production problems whereby you have inhibitors of SERCA, inhibitors of mitochondria, inhibitors of plasma membrane calcium ATPase, and that's going to lower your ability to make enough ATP to pump out calcium. So all those things are lowering your energy production capacity, your glucose oxygen delivery. And then simultaneously, you can increase the metabolic rate here. You can increase the metabolic rate by increasing the amount of glutamate in your diet, by psychological stress, by caffeine, by sleep deprivation, corticosteroid medications, tobacco, amphetamine stimulants, attention deficit medication stimulants. Glyphosate also functions as an excitotoxin because the glycine of glycine phosphate can bind to the NMDA receptor, increases activation. Being deficient in magnesium will cause increased NMDA activity, allowing more calcium into the cell. Beta amyloid protein can polymerize with additional beta amyloids. When it gets present in high amounts, or if there's LPS and LTA around, they'll cause it to form aggregates, which can push on the NMDA receptor and allow more calcium into the cell. So these can overactivate the neurons by thus increasing its metabolic rate, increasing the likelihood that the glucose oxygen delivery will not be able to match the metabolic rate adequately. So basically here they are at the same level, glucose oxygen delivery and metabolic rate. That's normal. If you drop the glucose oxygen delivery, now you're putting this neuron at risk because you're getting a bigger and bigger gap between the metabolic rate of the neuron and the glucose oxygen delivery. If you simultaneously ingest stimulants or do stimulant equivalents, like all these things we talked about, now the metabolic rate can get much higher than the capacity to deliver glucose and oxygen, also the capacity to produce ATP because of, like we mentioned, inhibitors of mitochondrial ATP production. There's over 50 of them. Many inhibitors of SERCA, sarcoplasmic endoplasmic reticulum calcium ATPase, or deficiencies of these essential nutrients, the magnesium and the potassium to run those sodium potassium ATP pumps. This gap gets too wide, these neurons will just die. They'll go into apoptosis. So this is one of the best things you can get out of this lecture. All of these things are increasing the likelihood your brain cells are going to die. So you want to avoid all these things if you can. For example, I think attention deficit medications for kids are kind of ridiculous. Okay, if you were to go on a street corner and sell amphetamines to somebody, that would be illegal. But then it's legal to give them to a kid. If you study the long-term consequences of them, you'll be surprised. They're much worse than is widely known. Okay, I jokingly made a mnemonic for this theory of dementia. I called it boast, because I'm kind of boasting that if you read like a neurology textbook, 1,700-page textbook on neurology coming out of Harvard, there'll be one paragraph on excitotoxicity under the context of epilepsy, seizure disorder, and one paragraph under the context of stroke. It should be a 50-page chapter, 100 pages on it. This is like the most important thing to know about. And I have a bunch of friends who are neurologists, and I talk to them about this stuff, and they don't know it because all doctors tend to just know the conventional textbooks because their boards exams are based on a conventional textbook. All of this stuff is in the medical literature, the scientific literature, but it doesn't get to the textbooks So they don't know it. And I have friends that are good neurologists, but they just never learned any of this stuff. It's not taught to them, even though it's essential to understanding the brain. It's basic, fundamental to understanding the brain. Okay, so this is just more detail of all the things that cause what we just talked about. Then I kind of made it this way, just kind of being funny. Excuse me. All right, so now if you look at the diets, how does this play out? We're almost done with this talk, but a couple things to show it all out. Typical American eating sort of a standard American diet, high in fat, high in oils. Most common cause of death, myocardial infarction, but high rates of impotence, cancer, diabetes, hypertension. You look at the East Asian culture, like, Japan, Korea, China, where they ate a lot of rice, but they still ate tons of sodium. And they also often smoked a lot of cigarettes. But they compensated with a lot of fruits and vegetables. So they get a lot of hypertension and a lot of strokes, but they still did relatively well. They didn't get much coronary artery disease because they were very low fat in their diet. And then you have a South Asian population, like people from India. And I was kind of surprised because almost all my Indian friends, they look healthy. They're skinny, pretty energetic. But what I found out is they have a very high incidence of coronary artery disease and of diabetes. And as a matter of fact, I'll just tell you one story. I have a friend, an Indian doctor, and I hadn't seen him for a couple of months. And I said, hey, how's it going? I haven't seen you in a while. What's new? And he goes, well, I was dead. I go, what do you mean you were dead? He goes, I was dead. He said, I had a myocardial infarction and I died and I got defibrillated and I came back to life. I go, really? I thought you were healthy. I thought you were a vegetarian. He goes, well, I pretty much am. And he eats a little bit of the ghee, the butter with saturated fat. And I said, I'll bet it's the oil. Do you eat fried food? He goes, oh yeah, sure. You have. He says, you have to cook with oil. How else are you going to cook? I go, no, you don't need to cook with oil. So here was a guy who otherwise would have been healthy, it seems. And he had a myocardial infarction and basically almost died. Luckily, he was able to be defibrillated right away, which is rare. Most people just die. That's a rare event. Okay. Anyways, low fat, low sodium vegan diet. You can see right here, they get hardly any type diabetes. If they actually are following the diet long term, they'll have like close to zero risk of type 2. And they'll be very unlikely to get hypertension, very, very unlikely to have a myocardial infarction, a stroke. And their incidence of cancer is also dramatically lowered. Okay. Nathan Pritikin would say going on his diet would lower the risk of cancer by 90%, according to Nathan Pritikin. But be that as it may, actually, the metabolic theory of cancer is much more useful than the somatic mutation theory. That's just another example where the prominent theory in conventional medicine is wrong. The metabolic theory is much more useful than the somatic mutation theory. We're not going to go into that. But the point of this is like winning the jackpot. Okay. You got diminished incidence of all the common causes of death. And so what I'm saying is a lot of people, they go, oh, so now you want to take away my ice cream. That's one of my few joys in life, my ice cream. When you tell them about the low-fat vegan diet, they kind of get this sense of giving things up, of making a sacrifice, that you're limiting the quality of their life. And that's the wrong attitude. The person who thinks that way is unlikely to be successful. The proper attitude is, thank God, there's something I can do. You mean I don't have to inevitably become sick and decrepit and pathetic and frail and weak and demented? No, there's a good way that you can get great odds to avoid almost all of this stuff. It's not 100% guaranteed, but there's as close to it as you're going to get in medicine and health. Okay, this is what I call the Spartan vegan pyramid. I kind of use the word Spartan because it's real cheap and simple and basic. And also because, I was formerly a wrestler, was my sport, and sort of a Spartan, simple way of doing things. And it's real simple. Do the basic stuff that kind of psychologically makes you healthy, plus get your sleep and get your sunshine and get your exercise, maintain your social relationships. Eat starches for the vast majority of your calories. That can be like 60 to 90 or 95% even of your calories. Eat some fruits in addition to that. Eat some veggies in addition to that. And you'll probably end up needing to take a vitamin B12. I take methylcobalamin. That's the only thing I take. And that's all you need. And that should keep you healthy. This is just kind of like what the plate looks like. Is also you want to filter your water, at least a carbon filter to get rid of the estrogenics. I like to have a reverse osmosis in the kitchen that also gets rid of fluoride and some other things. Plus, it's nice if you move to an area where you can get well water that doesn't have fluoride in it. And you make sure you test it first, of course, before you move there, but that also can help. What causes insulin resistance? We went through fat's the most important thing, but animal protein also is going to increase blood lipids, causing an anabolic phase in the blood, a synthesis that drives up blood lipids as well. The stress drives up blood lipids. Alcohol makes it worse. High fructose corn syrup makes it worse. Dairy is especially related to type 1, but it also contributes to type 2. We talk about ale in the water can damage the pancreatic beta cells. Fried food, the frying of the foods leads to hydroxynonenal, the Tetsumori Yamashima theory that decreases pancreatic beta cells, increases your risk of diabetes. And I think that's why a lot of these Indian people were skinny with diabetes, because they really had type 1.5, meaning a drop in their insulin production in their pancreas beta cells because of the complications of the omega-6 cooking oils. Let's see what else. Obesity related to the estrogenics. Obesity leads to hyperlipidemia, high blood lipids, and that leads to increased insulin resistance. There's a lot of estrogenic chemicals, like I said, I think that are contributing to people sometimes being confused about their gender, but also there is a fat storage hormone leading to weight gain, obesity, which then leads to hypertension and diabetes. So they're all working together to push in that direction. And then I talked about SERCA inhibitors, and also when SERCA is inhibited, that will also cause damage to the pancreas and increase the risk of diabetes. Okay, this is just showing percentage of fat. I'm a big believer you want to eat a real low-fat diet. There's no gain to eating all these fats. For example, nuts are 86% fat. Brazil nuts. Nuts in general, let's say in the ballpark, 80 to 90% fat. And I think Jeff Nelson did an incredibly great series of videos on nuts and the issues related to those, and on omega-3s. I highly recommend you watch those. They're the best thing anywhere you could find on the internet on those topics, on nuts and oils, omega-3s especially. Okay, I'm not a fan of soy. I know soy gets a lot of popular publicity. Any commercial food is going to have tons and tons of popular publicity because the industry's got $1 million budgets and they fund all these research studies to promote their product, okay? But all you got to do is look at it, okay? 40% fat. Why would I want that? Thousands of times more estrogenic than other things. I'm a former wrestler. I want to be tough. I don't want to be eating estrogenic fat, make myself fat, and then that's got estrogenic effect. That's the last thing I would want to eat, okay? And I'm not going to get into all the details of it. There's a whole science behind it, but if you look at the earlier papers, you'll see there's lots of problems before all the industry-funded papers came along saying how wonderful it is. Okay, look at these other animal foods. They all tend to be pretty low in fat in general. Oatmeal is like 15% fat, which is still pretty good. I like to keep my total fat below 10%. I don't even think about it or count it out. I just know it is by what I eat. And garbanzo beans are a little fat compared to other beans. They're about 13%. Lentils are probably the best bean. It's only 3% fat. Potatoes, sweet potatoes, white rice are only 1% fat. The reason I mention all those fat percent numbers is the lower the percent of calories you eat from dietary fat, the more likely you're going to be skinny. The skinnier the population will be. I actually think it's also good to keep your protein a little bit on the low side. And I say that because you decrease the workload of your kidneys. And don't get me wrong, I know there's a big difference between animal protein and plant protein. Animal protein has more leucine, has more methionine, has more activation of mTOR, et cetera, et cetera. And that plant protein is a lot better. Okay, fine. But anyways, I think sweet potatoes are the healthiest food in the world because they not only are very low in fat at 1%, they're also very low in protein at 4.5%. Human breast milk is only 5 to 6% at the most rapid phase of our growth. We don't need that much protein, okay? Nathan Pritikin also said, and Dr. McDougall agrees, you can't be too low in protein if you eat a naturally chosen diet. You can't be too low in fat if you eat a naturally chosen diet. So the other thing too is there's a lot of omega-3s in plant foods. My understanding of it after having read the literature on it is that you get enough from eating these plant foods. I don't think you need to be supplement on. That's just my impression from having gone through the research on that. So anyways, in summary, try to live simple like Adam and Eve, but keep your indoor heating and plumbing. And I think that's about the best you can do. I hope that was helpful.
Wow. Thank you, Peter. That was dynamite. All of this reminds me of those twin brothers from Canada, the Wilcox brothers that went over in 1975 to Okinawa and started the Okinawan Centenarian Project and studied, what they were eating and published a lot of studies on longevity and so on. And that's what this is. That's what you're basically describing. They've got the religion, the family, the community, the sunshine, the exercise, the very low-fat diet, the sweet potatoes. There's I know the women are the longest living, even longer than Loma Linda, people on the planet. Occurrence of dementia is zero practically. They've got lots of shortages of or in certain, let's say, minerals or vitamins or something like that, but doesn't seem to affect their longevity or their overall health. When you just look at the RDAs and that kind of stuff, but it's that very low fat diet. I love the opposite, what you say, the opposite of what you do, which is find the pill for the ill and send the bill, right? Isn't that the doctor profession?
The pill and send the pill. That's what they're trained to do. It's like, you're trained to sell drugs.
Exactly. Yeah. Well, that was great. That was terrific. I encourage people to get even more here or go over and watch, the individual chapters. You kind of gave a summary and overview and touched on everything, which is great, but you have a lot of practical advice. And, really, when you understand what's going on, it brings it home. I love the whole focus on blood viscosity. It's a simple way you sometimes describe it. To pump water to the brain is a lot easier than to pump a milkshake to the brain. And I mean, so true. And what makes the milkshake of your blood is all that extra fat. Look forward to having you back. Thank you so much.
Well, thank you.
Okay.